don't notice it at first. No one does. It is only a whisper on a monitor, one more faint pixel buried in the background noise beyond Jupiter's orbit, moving a hair faster than it should. But a computer flags the change, someone leans closer, and the night suddenly has a pulse. That smudge is not where it was yesterday. Its motion against the fixed tapestry of stars is too quick, too clean, too free. Within hours, the orbit begins to resolve, and with it a realization that rearranges your breathing. This object does not belong to us. It is falling through our sky on a path that isn't a loop, not a long cold ellipse that will one day bring it back, but a hyperbola, once only, crossing a visitor from the deep between. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, let me know in the comments where you're listening from and what time it is right now where you are. Astronomers will label it in the language of precision, through us Atlas, through R. For the third interstellar object we've ever seen Atlas for the survey that caught it, but to you in this first tremor of understanding it feels like something more intimate, a knock at the door in the middle of the night. You remember the first knock. Ni Oumuamua 2017, an enigma shaped by absence as much as presence. Brightening and dimming like a shard accelerating without an obvious tail, then gone, before we could agree on what we'd seen. You remember the second. 2I Borisov 2019, comfortingly comet-like, a proper coma and tail chemistry that felt familiar even as it carried the breath of another star. And now this third messenger, 3I Atlas, arriving with the soft authority of numbers and unbound path eccentricity, greater than one speed that doesn't belong to the clockwork of our familiar planets and debris. Already the mind splits into its two necessary rooms, the one with careful patient science, and the one where wild questions pace in the dark. Is it rock and ice, or something made? Which room will you spend the night in? You anchor yourself in the details, because details calm the imagination. The discovery, July 1st, 2025, by the Atlas telescope in Rio Hurtado, Chile, a NASA-funded sentinel sweeping the sky for anything that moves. The initial arc of observations narrow, then widening as data pours in from a chorus of observatories, professional and amateur, that trace the object's position from night to night. With every plotted point, the uncertainty shrinks, and the truth clarifies. This path is hyperbolic, a one-time flyby from interstellar space. The designation comes quickly, 3IC 2025 N1 Atlas, and the community exhales half in relief, half in awe. We've caught another one. We get to look again. Speed is the second seduction. At roughly 37 miles per second, about 60 kilometers per second relative to the Sun, it moves with a decisiveness our homebound comets rarely show. At that pace, it could cross the Earth-Moon distance in a couple of hours, and yet in the measureless stretches between stars this is still the tempo of patience. The numbers insist on two truths at once. It is unimaginably swift by human standards, and yet it has likely wandered for millions of years to reach us now. You picture that crossing a frost-dark object drifting past the crowded heart of the Milky Way through strands of dust no telescope will ever fully resolve, then tilting into our neighbourhood with all the indifference of a snowflake on an ocean current, indifferent except that we are here to notice. Third confirmed interstellar object sounds like a statistic until you let the rarity sink in. Think of all the sky we cannot watch, all the dim fragments that pass uncounted. Each detection is a lottery win made possible by new instruments, new surveys, new software that can catch a motion barely different from random noise and say quietly, look again. The Atlas system was built to shout when danger approaches, but just as often it whispers wonder. It whispered this one. And then, as it always does, it handed the baton to everyone else, Hubble above the atmosphere, JWST out at L2 with its cold golden eye, the great mirrors in Chile and Hawaii, the backyard telescopes that fill in gaps with stubborn devotion. A planet wakes as one organism. We point our eyes at the same travelling point of light. You can feel the two stories gathering. One is simple, beautiful, and already enough a natural comet ice dust-trapped gases shaken loose from another young star long ago wandering, until chance brought it here. In this telling, 3I Atlas is a postcard from a distant nursery. Its chemistry a fingerprint of temperatures and elements. We do not share its tale, a brief banner written in the physics of sunlight and sublimation. The other story is harder to hold without letting it run away from you. What if we are not just catching a fragment but noticing a choice? What if some other mind has thrown a seed into the currents, between suns, and it is gliding through our light right now. You know how quickly that question infects headlines, how ruthlessly it strips nuance from careful work. But you also know why it rises unbidden when the universe sends a stranger. For a moment, you let both possibilities breathe in the same room. Then you return to method. Method begins with motion. A hyperbolic orbit is not poetry, it is a calculation. Plot positions, fit a path, watch the residuals. If gravity alone explains the course with no need for maneuvers or miracles, you can stand on firmer ground. The early solutions make the case cleanly unbound, inbound, and soon outbound again. Perihelion will come near the end of October. Conjunction will hide it for a while in the sun's glare, and then, if we are lucky, the geometry will allow a little more study before the night takes it back. In the declarations and rumours to come, this is what you resolve not to lose the quiet satisfaction of seeing equations and photons agree. The sky is honest with patient listeners, and yet honesty does not mean simplicity. Even on the first nights, hints of strangeness creep in: how bright it is for its distance, or how faint, whether the coma is obvious or only a rumour of haze, how the light flickers over hours in a way that might tell you shape. You remember how badly we wanted time with Oumuamua and how little the sky gave us. You feel gratitude that this time the instruments are awake, coordinated, talking to one another. Hubble will try to fence the nucleus with upper limits. Webb will pry at the molecules, splitting the glow into chemical syllables, asking what froze where and when. Ground-based spectrographs will add their accents. Amateur stacks will reveal what professional pipelines sometimes miss. Nothing is certain yet except the thrill of beginning, so you stand in the doorway between science and story and make a promise to yourself. You will let the data lead. You will not forget what Interstellar means: not an omen, not a threat, but a direction, a history longer than anything your species has yet written. Third messenger, third chance to listen. You think of a comet's core as a kind of memory, a cold library of formation ices etched with the temperatures of a world we'll never see, dust seeded with the mineral grammar of another star. If 3i Atlas is only that it is already a wonder, a shard of elsewhere intersecting our lives for a handful of weeks, offering us nothing but its light, and in that light, the possibility of knowing more than we knew yesterday. That is enough to keep you awake. That is enough to be gentle with the night. And still, because you are human, you allow yourself one last question before returning to the instruments. What if we are wrong about how alone we are? What if the universe sometimes writes in straight lines and sharp angles, and we have simply not found the right grammar to read it? You smile at your own audacity, switch off the part of your brain that loves headlines, and turn back to the quiet work, centering apertures, rejecting bad frames, logging times to the second. Somewhere in the halo of that faint smudge is the answer to a very old question. You will not force it, you will wait and watch. And whatever it turns out to be ice or artifact, you will remember that this is how wonder should come to us, as a soft knock, as a breath held, as a small light moving against the stars. You have seen this story before, twice in fact. Once in 2017 when a slender shard slipped through the inner solar system like a thought crossing the mind of the universe. And again 2 years later, when a more familiar comet blazed its way past the sun in a brief radiant farewell. These were not myths, not whispers of UFOs or secret probes, but confirmed travellers from beyond the sun's dominion. And yet each arrival left a question half answered, as though the cosmos were speaking in riddles. Oumuamua came first, its name chosen from Hawaiian means scout or a messenger sent ahead. The Pan-STARRS telescope in Hawaii detected it on October 19th of that year, streaking through the inner solar system at nearly 87 kilometers per second. It was the first known interstellar object ever found, and nothing about it fit the textbooks. It was too bright for its size, too dry for a comet, and moved as if it were both falling and gliding at once. No tail, no coma, no spray of water, vapor, or dust. Just a thin beam of reflected sunlight that brightened and dimmed every few hours as though a long object were tumbling in the dark. Astronomers tried to fit it into familiar shapes, a cigar, a pancake, a shard. Each model made sense for a while, then collapsed under new data. The acceleration was the strangest clue of all, tiny but measurable, as though sunlight itself were pushing on a broad, thin surface. To most, it was a natural outgassing, too faint to see. To some, including Harvard astrophysicist Avi Loeb, it was a hint of engineering, perhaps a discarded light sail, a relic of technology adrift. The debate burned through headlines for months. a rare moment when orbital mechanics shared space with late-night talk shows, and when Oumuamua faded beyond our reach, it left behind a silence that felt personal, like a conversation cut short mid-sentence. Then in 2019, a second visitor arrived, but this one spoke a language we recognized. Discovered by amateur astronomer Gennady Borisov in Crimea, Tuj Borisov looked and behaved like a comet from the very first images, a nucleus sheathed in vapor, a tail unfurling in sunlight, the unmistakable chemistry of water ice, cyanide, carbon dioxide and dust. It was in a sense a reassurance, a reminder that interstellar objects need not all be strange. If Oumuamua was the riddle, Borisov was the translation. Here was a fragment of another solar system behaving exactly as physics said it should. Yet even in its normalcy, there was awe. We were seeing material born under another star built from a different balance of elements, surviving a journey across interstellar space intact. By the time 2I Borisov dissolved under solar heat and drifted outward again, the scientific community had begun to change. Suddenly, interstellar visitor was not a once-in-a-century miracle, but a category of field. Telescopes recalibrated their watch lists. Algorithms were rewritten to scan the sky for the faintest, fastest points of light. The search was no longer for whether there were more, but when the next would come. Because if there are two, there must be countless more wanderers cast out from forming systems crossing the galaxy like pollen on the wind. And now a third. 3I Atlas. A new messenger, faint and fast, its orbit unmistakably unbound. Each of the first two prepared us in different ways. Oumuamua taught humility, that the universe can still surprise us. Borisov taught patience, that sometimes the ordinary is miracle enough. But this third one brings something else, a synthesis of mystery and familiarity. It seems comet-like, yes, but not entirely. Its chemistry, its brightness, its behavior all carry the scent of anomaly. And so the cycle begins again. The telescopes awaken, the debates rekindle, and the same ancient question returns dressed in new data. What exactly is passing through our sky? It's easy to forget amid the graphs and press releases how improbable it is that we ever notice these visitors at all. Imagine a handful of dust crossing the span between stars, moving through the galaxy for millions of years, and our species existing for barely a cosmic blink happens to look up at precisely the right moment. That coincidence alone is reason enough for reverence. When Oumuamua left, it took with it our certainty. When Borisov came, it gave us a baseline. And when 3I Atlas appeared, it reopened both the rational and the impossible in equal measure. Because every messenger from elsewhere is not just a question about what lies beyond. It is a mirror held up to our need to ask, what if this one, unlike the others, refuses to fit into either box, natural or designed? What if it forces us to redefine both? So we watch again. From the observatories of Mauna Kea to the desert eyes of Chile, from the cold sentinel of Webb to backyard lenses tracing faint trails, the world turns its gaze to a single moving light. We remember the first two and whisper to the third, tell us your story, tell us where you came from, and tell us if you can what it means that we're here to see you. It begins as so many cosmic revelations do, with a sequence of small numbers and quiet patience. A faint point appears in the night sky, not remarkable at first, 19th magnitude, nearly invisible to the naked eye, but moving. Every night the telescopes return to it, measuring its position against the fixed grid of background stars. Each new image is a pinprick of light and a timestamp. Astronomers call this astrometry the art of turning motion into meaning. And as the positions accumulate, a pattern starts to emerge. The object isn't following the circular or elliptical dance that binds planets and most comets to the Sun. Its path is stretched, too stretched, an orbit that never closes on itself, a curve that opens like a door to infinity. At first, the differences are subtle, a matter of arcseconds, but in celestial mechanics, tiny deviations are everything. By the fifth night, the software that fits trajectories can no longer force the data to match a bound ellipse. The numbers push outward, the curve refusing to loop back. Then comes the decisive calculation eccentricity. Every orbit has one. A perfect circle measures exactly 0. An ellipse sits somewhere between 0 and 1. The farther from 1, the more stretched the orbit. Comets from the Oort cloud, the great icy halo around our solar system, sometimes reach 0.9999, almost but not quite escaping. But when the data for this new object settle above 1, greater than 1, the verdict is inescapable. This is not a visitor from the Oort cloud. This is a traveller from the void between stars. To understand the weight of that number, you have to remember what gravity does. It binds. Every planet, asteroid and comet you've ever heard of is held by the sun's pull, their paths curved just enough to bring them home again after every long cold journey. Even the most distant objects in the Oort cloud are still part of that family, loosely tethered, but tethered nonetheless. An eccentricity of exactly 1 would mark the fragile boundary between staying and leaving a parabolic path, the escape velocity achieved but not exceeded. Above 1 means freedom. It means the object is moving too fast to ever be captured. The sun's gravity will slow it, bend it but never turn it back. It will enter flash in our skies and vanish forever. Imagine the perspective of the scientists at Atlas in those first nights, watching the orbit fit evolve in real time. Each new observation narrows the uncertainty bars and the curve widens a little more, until the realization arrives almost with disbelief: this thing is not ours. Its speed relative to the sun is about 61 kilometers per second, faster than Earth's orbital motion, faster than most known comets. No gravitational nudge from Jupiter or Neptune could have thrown it to such velocity. Its approach vector doesn't line up with any of the long-period comet reservoirs we know. It comes from nowhere we can name, from a direction near the constellation Hercules, carrying the momentum of another star system's birth. A fragment exiled long ago now, wandering through ours by coincidence. Once that verdict sinks in, the whole network of skywatchers mobilizes. Dozens of observatories turn toward the coordinates. Each measurement sharpens the orbit, and with it the narrative. Soon, orbital solutions from independent teams converge on nearly identical results. Perihelion at roughly 0.8 astronomical units inside Earth's orbit, followed by a clean escape trajectory that will carry it beyond Neptune in a few short months. An unrepeatable encounter. The calculations spread across servers and message boards, accompanied by that rare mixture of scientific rigor and childlike wonder. The data do not lie. We are seeing an interstellar object again. For the public, hyperbolic may sound abstract, a mathematical curiosity, but to astronomers it is the cosmic equivalent of a passport stamped foreign origin. A hyperbolic orbit has no return ticket. Its shape on a graph is open-ended, the mathematical mirror of exile. If you were to draw it in chalk on the ground, it would never loop back toward the starting point. It would keep diverging wider and wider until it vanishes off the edge of your page. That open geometry is a signature, the geometry of escape. Still, astronomers are careful. They know how easily small uncertainties can masquerade as miracles. For a few days, they double-check. Could this be a comet from the Oort cloud, given an extra kick by Jupiter? Could gravitational perturbations have exaggerated its eccentricity? They run simulations backward in time, propagating its path through the solar system's gravitational field. The answer comes back clean. The object was moving at interstellar speed before it ever entered the planetary region. It didn't get fast because of the sun. It was already fast, already free. You can almost picture it long before our telescopes noticed. For millions, perhaps billions of years, it wandered the dark between stars, crossing the empty gulfs where light from no sun could warm it. Maybe it was born in the icy outskirts of another solar system, thrown out by the tug of a young giant planet. Maybe it has crossed through other systems before ours, unseen, each pass stealing a fraction of its mass as sunlight or stellar winds chipped away at its frozen skin. Now, by chance, it has intersected our tiny patch of the galaxy. For a few months we get to trace its curve, learn its composition, and then watch it fade again into interstellar night. The beauty of orbital mechanics is that it doesn't care for rumour or speculation. Whatever else we might say about 3I Atlas comet artifact or something between its motion is the purest truth we have. Those coordinates, those timestamps, that widening hyperbola, all unambiguous. Each photon that struck a detector in Hawaii or Chile or Arizona added its weight to the evidence. That faint smudge of light, at first just a curiosity on a survey feed, became through persistence a mathematical statement: eccentricity greater than 1, velocity exceeding solar escape, trajectory inbound from the galactic field, outbound forever. A visitor, not a resident. A messenger that will never return. And for the astronomers who first traced its path, that knowledge carried both pride and melancholy. Because once the numbers close, the story begins to end. You can predict every future position, where it will be next week, next month, next century, but you cannot follow it forever. It will leave us behind, as all hyperbolic travellers do, We are left with the curve on a screen, a thin line across the solar map that says simply and irrevocably not from here, not. Speed in space is rarely dramatic to the eye. There are no streaks, no sonic booms, no air to tear against. Yet when astronomers began plotting 3i Atlas's motion, in the weeks after its discovery, they realized it was moving through the solar system at a pace that could humble imagination itself. 61 kilometers per second relative to the Sun, more than twice the velocity of Earth's orbit, fast enough to traverse the distance from here to the Moon in just over 2 hours. To a human mind raised on terrestrial scales, those numbers mean little until you translate them into the language of time and distance. In the time it takes you to blink, this traveller covers tens of kilometers. By the end of a single night's observation, it has shifted across the frame like a bullet through still air. It's that velocity that immediately separates an interstellar wanderer from the millions of bound comets and asteroids that share our neighbourhood. The solar system is a gravitational well. Anything born within it moves under the Sun's long reach, slowed and turned by its pull. Objects ejected from the Oort cloud, the most distant shell of icy bodies, can come screaming inward after eons, but even they arrive with speeds that gravity can eventually reclaim. They loop, they return, their orbits close like ellipses drawn by a steady hand. 3i Atlas does not. Its energy is too high, its path too open. You can think of the Sun as a storyteller with a fixed vocabulary. This object is speaking in a foreign tense. The geometry confirms it. As it entered the inner solar system, Atlas approached from above the plane of the planet, slicing downward on a steep trajectory that pointed roughly toward the constellation Hercules. Its incoming velocity, about 37 kilometers per second before solar gravity began to bend, it is almost exactly what we'd expect of an object drawn from the galaxy's general population of stars and debris. In other words, it wasn't accelerated here by any encounter. It was already moving that way, already bearing the speed of another home. That single fact rewrites the story. It means the Sun didn't give it its momentum, the galaxy did. When scientists talk about heliocentric speed, they mean velocity measured relative to the Sun's rest frame. For most comets, that value is modest, 10, 20, maybe 30 kilometers per second, at perihelion when the Sun's gravity is doing most of the pulling. For Atlas, even accounting for that pull, the numbers refused to drop below the escape threshold. At every point in its orbit, its energy remained positive, an accountant's way of saying it would never be in debt to the Sun's gravity. It will leave just as fast as it came, trailing only a faint exhalation of dust to prove it was ever here at all. This speed isn't reckless, it's ancient. To reach it, an object must have been born in motion, perhaps flung outward by a giant planet in its native system, or by the collective tug of neighbouring stars in a dense cluster. Over millions of years, these slingshots add up. Whole populations of fragments are ejected into the interstellar dark, drifting with the ambient velocities of their local stellar streams 20 to 100 kilometers per second, each following its own trajectory through the Milky Way's gravitational field. Our Sun, moving at 230 kilometers per second around the galactic center, occasionally passes near these invisible drifters, and when one happens to intersect our orbital path, we see it briefly illuminated by our light, a frozen seed crossing our garden. The raw numbers of 3i Atlas tell an origin story written in momentum. Its inbound vector suggests it came from a region not far from the galactic plane, its velocity matching that of the local standard of rest, the average drift of nearby stars. That match is poetic. The object isn't racing ahead or lagging behind. It's travelling alongside the galaxy's slow current like a leaf on a wide river. The Sun simply moved into its path. That's why these encounters are so rare and so precious. Both we and the comet are in motion, two moving targets, in a dance that took eons to align. But numbers have a way of inviting imagination. 61 kilometers per second, what drives such speed? Some journalists seized on the figure to hint at intention, as though propulsion might be hidden inside. But orbital dynamics leaves little mystery here. The same equations that describe our spacecraft describe comets too. If Atlas were under any artificial thrust, its trajectory would show deviations too large to hide. Instead, its path fits gravity perfectly. No engines, no steering, just inertia, vast and ancient. The too fast of 3i Atlas is not evidence of design, but a testament to distance. When you start your journey light years away, even drifting becomes flight. And yet there is something undeniably moving in the idea of an object that has crossed interstellar space to reach us by accident. Consider what that means in time. At its current speed, it would take about 10,000 years to travel 1 light-year. If it came from a system a few dozen light-years away, and many do, then this fragment has been on the road for hundreds of thousands of years, maybe more. Before humans carved symbols into stone, before mammals ruled the continents, this icy rock was already gliding toward us through the void. It didn't choose the destination. The galaxy did. When astronomers first plotted the curve and saw the unmistakable energy signature of an unbound orbit, they felt that familiar shiver the moment when data stops being abstract and becomes narrative. A routine comet can be catalogued and forgotten. An interstellar one demands a new category, a new question: what world birthed this speed? Somewhere around another sun, it was part of a larger system. Maybe an unfinished planet, maybe debris from a collision. A gravitational nudge gave it freedom, and now, after 1,000,000 years of silence, we see it for a few weeks and call it by name. To most, it is just another comet. To the patient watcher, it is evidence of connection, that stars share their debris, that no solar system is an island. The velocity that sets it apart is also what binds us to it. Its momentum is the same physics that keeps our planets in orbit, that carried the Voyager probes outward, that moves the Sun itself through the Milky Way. 3-Sign Atlas's speed doesn't just break the rules of our solar system, it reminds us that our rules are local, parochial, fragile. The galaxy plays a larger game, and we have just caught a glimpse of one of its pieces mid-move. So when you hear 60 kilometers per second, don't think of violence or urgency. Think of inevitability. Think of motion older than language. That speed, that geometry, that unbound orbit, they are the handwriting of the cosmos itself, the signature of elsewhere written across our sky. For a few months we can read it. Then, as always, the messenger will slip away, taking its speed with it, and we will be left again with the quiet knowledge that not everything that passes through our heavens was ever ours to keep. Every field has its iconoclasts, those who refuse to stay within the neat margins of accepted thought. In modern astrophysics, that role often falls to Avi Loeb, a Harvard professor with an easy smile, a quiet voice, and a gift for turning cautious data into provocative questions. When 3i Atlas appeared in the survey feeds, most astronomers saw a comet, odd yes, but explainable. Loeb saw a pattern, a whisper of déjà vu. He remembered 2017, the moment the world first heard the name Oumuamua, and how one strange acceleration turned a fragment of rock into a global controversy. He had been at the center of that storm, arguing that science should not dismiss the improbable simply because it feels uncomfortable. And now, with Atlas tracing a similarly puzzling curve across the sky, his voice returned to the conversation, calm, measured, and disruptive all over again. Loeb's position, though often mischaracterized, is surprisingly modest. He doesn't claim certainty. He rarely even claims probability beyond the tiniest margins. Instead, he insists on the permission to ask. In interviews, he framed the question this way: if there's even a 10% chance that something like this could be artificial, shouldn't we take it seriously? 10% not proof, not proclamation, but an invitation. To his critics, that phrasing was reckless, a spark tossed into the dry grass of public imagination. To his supporters, it was courage, a reminder that scientific progress depends on those willing to ask the questions everyone else is too careful to utter aloud. The number itself, 10%, is meaningless in a statistical sense. It's not derived from Bayesian models or spectral analysis. It's rhetorical, a placeholder for uncertainty. But it carries power because it translates wonder into language the public can grasp. A 10% chance is something you can picture. It's small enough to be credible, large enough to be thrilling. Headlines need that balance. Within hours of Loeb's comment, the story metastasized across social media. Harvard scientist says alien technology possible. The nuance that he was merely keeping the door open evaporated. In its place grew a narrative of defiance, Loeb versus the establishment, the bold truth-teller challenging orthodoxy. Inside the scientific community, reactions were as polarized as any political debate. Some rolled their eyes, weary of the same pattern, since Oumuamua Loeb making cautious speculation sound like revelation. Others admitted privately that his provocations served a purpose. They drew attention, funding curiosity. After all, speculation is the lifeblood of inquiry. One astronomer joked that Loeb was like caffeine for science, occasionally jittery, occasionally overstimulating, but impossible to ignore. He reminded the public that behind the calm language of data lies a field still capable of wonder. For Loeb, the argument was philosophical as much as empirical. He pointed out that the search for extraterrestrial intelligence, the CT legacy stretching back to the 1960s, has always assumed that detection would come from a signal, a radio wave, a beacon. But what if civilization sent objects instead of messages? What if debris is their calling card? We keep waiting for them to speak, he once said. But maybe they've already sent packages and we just haven't recognized them. That line, equal parts poetry and provocation, traveled farther than any spectrum analysis ever could. It caught imaginations. It also infuriated traditionalists who feared that the alien label would taint serious research with tabloid sensationalism. Yet in quieter rooms, the debate isn't about aliens at all, it's about epistemology. How do we know what we know? How wide should the aperture of curiosity be before it collapses under its own speculation? Loeb argues for openness. Science is not about belief, he writes, it's about evidence. But we cannot find evidence for things we refuse to look for. To him, the 10% is not a bet on aliens, it's a bet on humility, a recognition that the universe is older, stranger, and more inventive than our catalogues can encompass. To ignore the possibility, however remote would be, to declare prematurely that we have nothing left to learn. Still, many scientists counter with a warning of their own. The problem isn't curiosity, it's context. In a media ecosystem that thrives on exaggeration, even a whisper of alien becomes a shout. What begins as an open question turns into a headline war. The rigor of the process gets lost amid the noise, and the tragedy, they argue, is that this noise often drowns out the real wonder that a natural interstellar object is itself extraordinary. Why reach for fiction when reality already surpasses it? But Loeb's contrarian spark refuses to go out. He founded the Galileo Project, an initiative designed to systematically search for evidence of extraterrestrial technologies, not through belief, but through instrumentation. Telescopes optimized for anomalies, cameras scanning the skies for what traditional surveys might overlook. His message is clear: skepticism should never become blindness. If the universe is giving us visitors, he says we owe it the courtesy of paying attention. And so his 10% lingers not as an equation but as a challenge. It splits rooms, fuels arguments, and lights up dinner conversations across observatories and online forums. Because deep down, everyone recognizes what that small number represents: the hunger for meaning, the wish that the vast silence of the galaxy might finally answer back. A mere sliver of possibility is enough to make us listen harder, look longer, dream bigger. It is the ember that keeps the night alive. In the end, whether 3i Atlas proves to be ice or artifact may matter less than what the question itself awakens in us. Loeb's 10% is not really about aliens. It is about attention, the discipline of wonder, the refusal to let familiarity dull curiosity. Even a scientist hardened by data knows that every revolution in understanding began as heresy once. And so, amid the spreadsheets and orbital plots, the whisper remains: what if? That's all it takes: a fraction, a rumor, a 10% chance to remind us that discovery is not just a method, but a state of mind. Science, for all its wonder, is a discipline of patience. When a faint visitor like 3i Atlas drifts into our skies, astronomers do not chase headlines, they chase evidence. To do that, they turn to their instruments, to the ancient quartet of observation that has quietly rewritten our understanding of the universe: astrometry, photometry, spectroscopy, and imaging. These are the 4 keys to truth, each unlocking a different aspect of the same enigma, each turning light into understanding. They begin with astrometry, the oldest of the 4 and the backbone of celestial certainty. It's the art of tracking position and motion with exquisite precision, pinning a moving speck of light against the still canvas of stars. Every night, telescopes record 3 Atlas's coordinates down to fractions of an arcsecond. Those positions, plotted over days and weeks, reveal the orbit's exact curve through space. If the path fits gravity's equations perfectly, it tells us that natural forces alone are at work. But if the motion deviates, accelerating where no outgassing is seen, curving in ways no gravitational pull can explain, it would raise an eyebrow. This is how we caught Oumuamua's subtle acceleration years ago, and why Atlas's trajectory is now under equal scrutiny. Astrometry, in its quiet way, is the language of motion, and motion rarely lies. Then comes photometry, the science of brightness. Every time sunlight reflects off the surface of a comet, or dust glows in the warmth of the sun, it creates a pattern of light that waxes and wanes as the object tumbles. By measuring that variation, how quickly it brightens, how sharply it dims, astronomers can infer shape and rotation. A spherical comet produces a smooth rhythm. An elongated shard creates deep asymmetric dips. When Oumuamua's brightness swung tenfold over its spin cycle, the world glimpsed its strangeness. Now, as Three-Eye Atlas flickers in its own uneven rhythm, photometry again becomes a kind of X-ray mapping geometry without ever seeing it directly. The cadence of those light curves tells us if we're watching a natural lumpy rock or something that glints too precisely too regularly, something that might in theory have edges. But brightness and motion only hint at what an object is. To know what it's made of, scientists must split its light. This is spectroscopy, perhaps the most powerful of all the tools. When sunlight bounces off a comet, it carries the chemical fingerprint of the gases and dust it has touched. Through a spectrograph, that light separates into rainbows sliced by dark or bright lines, each one belonging to a molecule or atom. Water leaves its mark near 308 nanometers carbon monoxide, at 4.7 microns carbon dioxide near 4.3. It's a cosmic barcode. In Three-Eye Atlas's case, those lines tell a curious story: an abundance of carbon monoxide and carbon dioxide, and far less water than expected. That absence alone doesn't make it artificial, it makes it different. A comet forged in a colder system would lock away carbon gases more easily, leaving water scarce. But spectroscopy is how we know. Without it, everything else is guesswork. Yet there's another reason scientists love spectra: they can also expose the impossible. If, for example, light revealed metals vaporizing at impossible temperatures, or emission lines from elements arranged in non-natural patterns, laser-like coherence, or polished alloys, unknown in nature, that would hint at something engineered. So far, Atlas has yielded nothing of the sort. No signals, no manufactured chemistry, only the raw poetry of alien ice. Still, the absence of anomalies is itself data, and data is how mystery becomes meaning. The fourth key, imaging, seems the simplest but carries its own quiet power. At first glance, it's just photography: turn the telescope toward the target and take a picture. But these are not snapshots. They are layered exposures stacked and filtered, corrected for atmospheric wobble, aligned with sub-pixel accuracy. Each one sharpens the faint halo around the nucleus, the coma, and the tail that spills away under sunlight. With Three-Eye Atlas, the images show not just a tail, but a faint anti-tail dust appearing to stream sunward. It's an illusion of geometry caused when Earth crosses the plane of the comet's orbit, but still it looks uncanny. To an untrained eye, it could be mistaken for a directional beam. To scientists, it's another reminder that perspective is everything, that nature often mimics artifice in its own elegant way. Each of these methods works alone, but their real strength is in harmony. Astrometry nails the orbit. Photometry reveals shape and spin. Spectroscopy decodes chemistry. Imaging provides context and scale. Together they build a portrait, not a photograph, but a reconstruction of truth drawn from light itself. Think of them as senses. Astrometry is sight measuring where a thing is. Photometry is hearing catching its rhythm. Spectroscopy is taste sampling its ingredients. Imaging is touch giving it form. When all four agree, certainty begins to bloom. The first results from these tools have already begun to converge. Atlas's path obeys gravity. Its brightness wobbles like a natural tumbling body. Its chemistry is exotic but not impossible. Its images, though eerie, show dust and gas, not polished surfaces. If there is a secret inside this traveller, it hides behind physics that looks so far familiar. Yet familiarity does not mean dullness. These tools are not just detectors. They are translators, turning faint photons into sentences we can read. And those sentences tell us that even when the extraordinary is natural, it is still extraordinary. That is why astronomers wield their instruments with both skepticism and reverence. They are not searching for miracles, they are searching for precision. Because to prove that something is an alien requires the same discipline as proving that it is. Each measurement narrows the gap between imagination and fact. Each photon captured is a note in a symphony of understanding. And if someday those notes form a melody that doesn't fit any natural scale, these same instruments will be the first to sing it. For now their song is simple but not small, a visitor from another star obeying gravity, reflecting sunlight, whispering through data that truth, even when mundane, is miraculous. Spectroscopy is the art of turning light into language. Every photon that strikes a telescope carries a story, a coded memory of where it has been, what it has touched, and what elements shaped its journey. For astronomers, Three-Eye Atlas began to speak not through photographs but through the colors hidden inside its faint shimmer. Split that light through a prism and you no longer see a simple glow. You see a barcode of the cosmos, bright and dark lines, each corresponding to a molecule, each a syllable in a chemical sentence billions of years old. When the first spectra of 3I Atlas came in, scientists expected the usual cometary signature, the broad water bands that dominate almost every icy traveller born of our sun's outskirts. But as the data trickled in from Hubble and ground-based observatories, something strange emerged. The waterlines, those reliable fingerprints at ultraviolet wavelengths, were faint, almost absent. Instead, two other voices rang clear: carbon monoxide CO and carbon dioxide CO2. The ratios were unlike anything typical of solar system comets. Here, carbon-bearing ices shouted while water only whispered. To understand why that matters, you have to know how comets are built. They are fossils of their star's nursery, frozen samples of the chemistry that once swirled around a newborn sun. In our solar system, comets condensed in the outer regions near the Kuiper belt and Oort cloud, where temperatures hovered around 30 to 50 Kelvin, cold enough for water to freeze solid, but too warm for gases like CO and CO2 to dominate. Those volatile molecules can only remain frozen in even colder places farther from a star's warmth regions near 20 Kelvin, or below where the light of the parent sun is so faint it could barely cast a shadow. So when 3I Atlas revealed a composition rich in carbon monoxide and dioxide but poor in water, it told a story of origin, a birthplace colder, darker, and more distant than anything in our solar nursery. It likely formed far beyond the frost line of its home system, perhaps in a realm analogous to our own scattered disk, or even the interstellar medium between stars. In that deep freeze, CO and CO2 ices accumulated, easily coating dust grains before they merged into kilometre-scale bodies. Water, by contrast, may never have condensed there at all. The chemistry of Atlas isn't an accident, it's a map. Spectroscopy doesn't merely catalogue ingredients, it measures ratios, and those ratios are the fingerprints of worlds. The proportion of carbon to oxygen, the strength of certain emission lines, the subtle shifts caused by isotopes, all of these let scientists infer temperature, pressure, and even the radiation environment in which the object formed. For Atlas, the data painted a picture of a comet born under a dimmer sun, perhaps orbiting a red dwarf, or a distant companion star where light was scarce. Its molecular composition suggests a region with little ultraviolet radiation where carbon compounds could survive unbroken for eons, in other words, a cradle at the galaxy's colder edge. That realization sends a quiet thrill through the scientific community, because it means chemistry can travel. Every interstellar visitor is not just a rock, but a message, a frozen archive of the conditions around another star. When we look at 3I Atlas through our spectrographs, we are effectively reading the temperature of a foreign sunrise that no human will ever see. We are tasting the air of another world, one that froze solid long before Earth had oceans or oxygen. The details deepen the intrigue. In addition to the carbon-rich gases, astronomers found hints of dust grains that were unusually fine, smaller and smoother than the ones typically blown off comets in our solar system. Such grains scatter light differently, producing a coma that glows with a subtle blue tint reminiscent of the cold reflection nebulae seen in interstellar clouds. It is as though 3I Atlas carries not just the chemistry of its origin, but the texture of it, a softness born from deep cold. Water's absence also has implications for its activity. Most comets erupt into visible glory when they near the sun because water ice sublimates easily at a few astronomical units. But Atlas began outgassing far earlier, farther from the sun than expected. That's because CO and CO2 sublimate at much lower temperatures. They turn from solid to gas while still deep in the cold. So this visitor began shedding gas long before it crossed Earth's orbit, creating a coma driven by exotic volatiles rather than the familiar steam of melting water. Even its behaviour defied our habits. Some skeptics initially wondered if the low water signal meant artificiality, perhaps a metallic surface reflecting sunlight rather than ice evaporating. But spectroscopy settled that quickly. The emission lines matched molecular transitions, not alloys or plasma arcs. The comet was breathing gas, not shining metal. The alien quality lay not in design, but in distance, a natural body from an unnatural neighbourhood. And here lies the quiet poetry of science, the way precision turns into awe. Because in the pattern of light, astronomers saw not evidence of aliens, but something in many ways more profound proof that the building blocks of planets vary from star to star. That our solar system's recipe is not universal, but one of countless local dialects in the language of matter. Atlas spoke with an accent we hadn't heard before. The James Webb Space Telescope deepened that conversation. Its infrared instruments detected faint thermal emissions that matched the presence of CO and CO2 ices, sublimating simultaneously a phenomenon impossible in comets born here. Its spectrograph also revealed trace organic, simple hydrocarbons that form under cosmic radiation in the cold. Nothing engineered, but everything extraordinary. To Webb's golden eye, 3I Atlas was a frozen chemistry experiment conducted in another corner of the galaxy, now unfolding before us like an opened vial. So when scientists say its chemistry is unusual, what they mean is that it carries fingerprints of a world colder than ours, a world where carbon ruled and water was scarce, where the sunlight was weak and the night eternal. That realization collapses the distance between systems. It means we are not studying a stranger. We are meeting kin, a fragment of a process that happens everywhere endlessly in a galaxy of 100 billion stars. Spectroscopy in the end is empathy disguised as mathematics. It allows us to recognize ourselves in the unknown, to see that the light from an alien ice ball can speak across light years in a dialect we still understand. And through that conversation we learn that difference is not mystery, it is diversity. 3 Atlas, cold and carbon-rich, is the galaxy reminding us that its imagination is broader than ours. When the first stacked images of 3I Atlas arrived, astronomers noticed something unsettling. The tail, that signature of all comets, a luminous brushstroke of dust and gas sweeping away from the sun, seemed to be doing something impossible. It wasn't just pointing outward as radiation pressure dictates. A faint secondary streak appeared to reach toward the sun, as if the comet were exhaling in both directions at once. Within hours, headlines followed "Comet defies physics," but physics had not been defied. It had only been misunderstood, or rather misseen. The truth was stranger in a quieter way. What the telescopes captured was a geometry trick called an anti-tail, a phenomenon both real and deceptive caused by alignment and perspective. In the vast emptiness of space, even a few degrees of viewpoint can turn a sheet of dust into an arrow, pointing the wrong way. To understand it, picture the comet as a painter scattering fine particles along its orbit as it travels. Those grains don't vanish when released. They linger following the same curved path around the sun. Over time, the orbit becomes a thin ribbon of dust, like the trail left by a boat on still water. Normally, we view that ribbon from the side and it looks like a classic tail, a streak flowing away from the sun, sculpted by light pressure and the solar wind. But sometimes, for a brief moment, Earth crosses the comet's orbital plane and looks almost edge-on through that sheet of dust. From that angle, the geometry folds. The dust that trails behind can appear to point forward, converging toward the sun from our perspective. A mirage written in sunlight. It's rare but not unique. Comet Arend Roland did it in 1957, baffling early observers until orbital models explained the illusion. Comet Pan-STARRS repeated it in 2013. And now, 3I Atlas, our interstellar wanderer, joins that small family of optical deceivers. When the Hubble Space Telescope's images showed a main tail streaming outward and a faint ghostly filament reaching sunward, scientists recognized the telltale configuration immediately. Not defiance geometry, not intention alignment. Yet there is something undeniably eerie about the image. 2 luminous plumes in opposite directions, one golden, one bluish, curving like outstretched wings. To the public imagination, it looked engineered symmetrical, as if the object were broadcasting light. Even experienced astronomers paused for a heartbeat before analysis took over. That moment of wonder, that brief surrender to strangeness, is not a flaw. It's the beginning of curiosity. Science doesn't exist to extinguish awe. It exists to explain it without erasing its beauty. The mechanics behind it are simple, but the picture they create is intricate. The main tail, made mostly of ionized gas, always points directly away from the sun. Solar wind drags those charged particles outward like smoke in a breeze. The second component, the dust tail, behaves differently. Dust grains are heavier, slower to respond and more bound to the comet's orbital motion. They form a curved arc that lags behind. When that arc lies nearly in the same plane as Earth's line of sight, sunlight scattered off its surface can overlap, creating a bright ridge that appears to aim toward the sun. It's a play of angles and distant celestial parallax on a cosmic scale. In reality, nothing in the comet is reversing direction. Each particle of dust continues along its predictable path, obeying gravity and the pressure of photons. The comet isn't steering, it isn't sending signals. It's simply performing the same quiet physics that every comet does, only from an angle we rarely see. And because 3I Atlas is interstellar, the curiosity multiplies. We're not just seeing an illusion, we're seeing how a fragment from another star interacts with the same sunlight that warms our oceans. It's the universe holding up a mirror reminding us that perspective changes everything. For scientists, anti-tails are precious opportunities. They reveal the structure of the dust sheet, the size of particles, and even the rhythm of the comet's shedding. By studying how the false tail brightens and fades as Earth moves through alignment, researchers can map the thickness of that debris plane and infer how long ago each particle was released. In the case of 3I Atlas, that analysis suggests a slow, steady loss of fine carbon dust, another clue linking its chemistry to the cold, carbon-rich birthplace hinted at in its spectra. To the untrained eye, though none of that nuance matters, all one sees is the impossible, a tail pointing the wrong way. And maybe that's fitting, because interstellar visitors always arrive bearing a touch of impossibility. They remind us how often truth hides behind appearance, and how perspective, whether of a telescope or of the human mind, can turn ordinary physics into revelation. So the next time you see an image of 3I Atlas with its twin plumes stretching across the black, remember that you're not witnessing a violation of natural law but a celebration of it. You are seeing light, dust and motion conspiring to trick the eye, a small miracle of alignment billions of kilometers wide. Even in illusion, the cosmos teaches us something true, that wonder is not diminished by understanding. If anything, comprehension only sharpens the awe. Because the tail that seems to point wrong is really showing us how right the universe is, precise, patient, and infinitely capable of surprise. When you cannot touch a thing, you learn to read its light. For 3I Atlas, that meant watching how its brightness rose and fell night after night, pixel by pixel as it spun through space. Astronomers call this record a light curve, a time-lapse of reflected sunlight plotted against hours and days. At first glance it looks like noise, a jagged line with small humps and dips. But inside those fluctuations lies a physical portrait, the object's shape, its rotation, even its texture. Light, after all, obeys geometry. Each time a larger or more reflective facet turns toward the sun, the comet brightens. Each time it shows its shadowed side, it dims. The pattern repeats like a heartbeat, whispering the story of form in the language of photons. For most comets, that rhythm is gentle, a few tenths of a magnitude between peaks and valleys, a signal of near roundness or slow rotation. But 3I Atlas behaved differently. Even early measurements hinted at a wider swing, a brightness variation greater than a factor of 2. Not as dramatic as Oumuamua's, but enough to suggest something elongated, tumbling rather than smoothly spinning. That irregular flicker told observers they weren't looking at a neat sphere of ice. This was a fragment, a shard. Somewhere in its past, perhaps during ejection from its parent system, something violent had twisted it, cracked it, made it asymmetrical. Comparisons to Oumuamua came quickly. Back in 2017, that first interstellar visitor's light curve had shocked scientists with its amplitude tenfold changes in brightness every 8 hours, implying a body at least 6 to 10 times longer than it was wide, like a flattened cigar or a cosmic surfboard somersaulting through sunlight. That extreme elongation, coupled with its smooth acceleration, was one of the details that fueled Avi Loeb's speculation about artificial origin. No natural object, some argued, should look or move like that. And yet later models suggested it could a fragment of nitrogen ice perhaps, or a thin flake chipped from a larger body and eroded by cosmic rays. The universe, it seemed, had room for strange shapes without human help, so when 3I Atlas began flashing its own uneven rhythm, astronomers looked carefully wary of déjà vu. The pattern was subtler but real. Its peaks were not evenly spaced, its troughs irregular, suggesting not a simple spin but a chaotic tumble. Imagine a snowflake caught in a slow, weightless drift, turning end over end so that no single face remains sunlit for long. In the emptiness between stars, such motion can persist for millions of years. No friction to slow it, no atmosphere to stabilize it, only sunlight nudging ever so slightly, sculpting brightness into code. To the eye of a scientist, this was pure information. To the human imagination, it was something else. A flickering light curve feels alive, a pulsar signal, a Morse code across the void. When data points oscillate in steady rhythm, even randomness starts to sound like intention. It's how we are wired. Our pattern-hungry minds can't help but listen for messages. But in astronomy, message often means moment of rotation. The pulse that seems like language is just sunlight playing across uneven terrain. There is no whisperer, only physics, and yet the whisper remains. The irregularity itself tells a deeper story. A tumbling rotation suggests the object has been disturbed by a collision, an outgassing jet, or the chaotic gravitational tides of ejection from its original star. No single event needs to be extraordinary. Cumulative chaos can do the work. Small torques over millennia can shift spin axes until the object's motion becomes complex, almost choreographed in its randomness. That complexity doesn't mean design, it means history. Every rotation is a fossil of past forces. When astronomers modelled 3I Atlas's light curve, the solutions multiplied. It could be an elongated nucleus, perhaps 500 meters long, or a flattened shard like a chipped slate, its long axis gleaming briefly as it caught sunlight. The brightness changes were consistent with an object rotating once every 12 to 15 hours, slower than Oumuamua but equally erratic. No artificial beacon here, just a relic that spins the way all broken things do unpredictably yet faithfully to the laws of momentum. Still, it is hard not to anthropomorphize it. A light curve that flutters irregularly feels emotional like breathing. As the peaks rose and fell, scientists at observatories plotted them late into the night, each one a heartbeat of a world they'd never touch. It's an intimacy that only distance can create. You learn to love an object through its faintest echoes. The flicker, too, holds practical power. By combining the light curve with spectral data, researchers can estimate the albedo, the reflectivity of its surface. A bright icy crust would reflect more, producing shallower troughs. A darker carbon-rich mantle would deepen them. Atlas's behaviour pointed to something in between dusty, rough, mottled like volcanic glass dusted with frost. It was irregular not just in shape but in reflectivity, patches of bright ice, interlaced with darker regolith, a pattern of contrast that mirrored its oscillating light. Oumuamua had taught us that irregularity doesn't have to be suspicious. It can be beautiful, even inevitable. Natural processes sculpt a symmetry with a patience no engineer can match. Collisions, sublimation, slow erosion by micrometeoroids. Perfection is the exception, not the rule. The cosmos thrives on imperfection, and yet narrative instinct persists. A tumbling shard from another star feels like metaphor, a messenger half broken, carrying both mystery and evidence. Its light curve becomes a kind of diary written in shadow, bright, when it shows its smooth face, dim when it turns its scars. We project meaning into that rhythm because meaning is what we do, but perhaps that projection is itself part of the story, proof that even when we study cold stones adrift between suns, what we're really measuring is the human desire to connect. So the scientists continue to watch the flicker, measuring its intervals, refining models, finding in those luminous waves the shape of a distant fragment. The light curve doesn't tell us everything, but it tells us enough. 3I Atlas is no sphere, no smooth craft, no perfect geometry. It is a survivor, irregular and true to physics, shaped by time, not intention. And in its imperfect pulse it reminds us that strangeness and natural law are not opposites, but partners, that even the most uncanny rhythms can emerge from silence, faithfully, beautifully, and without design. In the perfect clockwork of gravity, an object's path is governed by a single rule: fall. But comets are not perfect clockwork. They breathe. As sunlight warms their surfaces, ice is sublimed directly into gas and geyser, outward turning the nucleus into a tiny lopsided thruster. The result is a gentle push, so gentle it's measured in millimeters per second that nevertheless accumulates into kilometers of orbital drift. To a casual reader, that sounds like sleight of hand. To celestial mechanics, it's the most ordinary kind of magic force mass time. Start with the push itself. Gas jets act like rocket plumes. If a patch on the surface vents mass at a rate m, with exhaust speed vive the thrust is fm vf divide by the comet's mass, MEM, to get the acceleration to yablaye, fm lemmen, frac, demnyam, frac, deatmlevnyam, mvmv. Nothing exotic, just Newton's second law, and the reality that the venting is rarely symmetric. A smooth spherical comet with uniform jets would cancel its own pushes. Real comets are not smooth, and rarely uniform. One sunlit fissure outgasses harder than its neighbours, so the nucleus gets a persistent nudge in a preferred direction. Now put in numbers to feel the scale. Imagine a modest nucleus, a few hundred meters across, say radius r, 300 per sim, 300 pilours, and with bulk density, 500 klask m, through a trios, hoist, 500 joules text, ja, spejos, 3 or 500 kilos, kills gav 3, light porous ice dust mix. Its mass is m fosturipia fosfafdiektiantlus korg md hour just approximate frag 3 gas piatrino just 5.6 times ds test or text kiast. M34 PS 3R West Tinasten kilos. Suppose just one active vent shedding man yan kilas mias. Niesen des Jerax kilo minus 10 kilos is bien. A small garden hose of gas by cosmic standards with a characteristic outflow speed with 500 besms 1 vers mass in 500 gas. Text mist just 500 blast is 1. The thrust is then F factions just 3. NF gasim 5 best times 10 aus des just text and F best of 3 N. Spread across. Mappath the acceleration is a Nescankels test squared mess 2. Aid sim. Last times testing der skins textums custes. Is a tendas justice S2, that's less than a billionth of Earth gravity. Negligible not to orbits. Over one day, Devirus justus T is justus gestos testus casti at 400 S7 poloitis tithrisptus genstus delta vahaga astigius justim. It's just nets astas doesn't exist just 2 times 3 and 400 text ds to approximus teftas times ds 10 text down skip 1 to vestas test like yes stups t6 400 s7 test 3 may scan about 8 millimeters per second. Multiply by a month to 30 to 3 delta test deep text down to approximus 20 scan text stern 30 to 23 em s1. And the along track displacement under constant push becomes gestures 1282 3.0 Oscars de femmes gestus de frac 1 tustus dos grand repairs 3.0 times 10. And dexters 21 at 23.0 de pef to nearly 300 kilometers, a breath repeated becomes wind. This is the origin of non-gravitational acceleration in Comet ephemerides, the tiny extra term added to the gravitational solution so the predicted sky position matches reality. The effect shows up as small residuals when you fit astrometric data, those night-by-night RA deck positions. Fit a purely gravitational trajectory, and the predictions start to run ahead or lag behind the measured points by arc seconds that grow with time. Add a simple jet model, often parameterized with a few constants that scale with solar heating, and the residuals collapse. The mystery force becomes just sunlight vaporizing ice. Crucially, none of this implies guidance or intent. The push depends on which side is warm, not on where the comet wants to go. As the nucleus rotates, active areas turn into and out of sunlight, modulating the thrust like a slow strobe. If the rotation is simple, a single spin axis, the net effect over one full turn can partly cancel. If the motion is tumbling, some directions win out over others for weeks at a time, and the small mismatch integrates into a measurable drift. Either way, the sign of the push is written by thermophysics, albedothermal inertia, shadowing vent geometry, not by steering. You can feel the leverage of time even more starkly by scaling the numbers. Halve the radius to 150 mems, but keep m.s dot mem similar, and the mass drops by a factor of 8. The same jet then yields a 8 times larger. A few centimeters per second per day becomes plausible near perihelion, when activity peaks, and the monthly displacement climbs into the thousands of kilometers. Conversely, a kilometer-scale nucleus with the same jets hardly budges. Its mass damps the effect to barely a couple kilometers per month. Non-gravitational acceleration is therefore a sensitive ruler of size, activity, and spin state, which is why dynamicists care so much about modeling it. There's another subtlety direction. Orbital fits often decompose the non-gravitational term into 3 orthogonal components: radial away from the Sun transverse, along the direction of a motion, and normal out of the orbital plane. CO and CO2 ices can sublimate far from the Sun, so their jets can bias the transverse component long before a water-driven coma fully develops. A small positive transverse acceleration lengthens the comet's path and shifts where and when it appears on the sky. To an observer, that looks like the comet being late or early compared to a gravity-only prediction. Stack enough nights, and the lateness becomes a map of the jets. Because these pushes are seasonal, in the comet sense, the acceleration is not constant. It tends to follow an empirical heating law that rises and falls with heliocentric distance. Ephemeris software folds that into the fit, letting the acceleration peak near perihelion and fade outward. The sophistication can be minimal, a few parameters to capture a messy reality and still yield excellent predictions. Again, no conspiracy is required, only patience, and a model you're willing to adjust as new astrometry arrives. If you've heard claims that the comet changed direction, now you can translate. In practice, no sharp turn is seen, just a graceful continuous deviation that grows like T2 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 while the jets are active. Millimeters per second become tens of meters per second over months, and a line of predicted positions must curve a little more to keep up. The path remains smooth and entirely explicable by physics. If anything, comets are famously bad at hiding their thrust. They leave the evidence wrapped around them as a coma and tail. The mathematics, for all its tidy symbols, is a way of keeping ourselves honest. If there were a hidden engine or active guidance, the residuals would refuse to collapse under any reasonable outgassing law. The needed acceleration would be too coherent in direction, too insensitive to sunlight, too steady through rotation. Instead, what observers find over and over is messiness thrust that waxes at noon and wanes at dusk, a vector that wobbles with the spin, bursts when a crust cracks, lulls when an active patch rotates into night. The fit improves when you let the comet be a comet. There's a quiet beauty to this. Imagine that nucleus up close, a dark carbon-dusted surface, vents fringed with hoarfrost jets unspooling like white threads into black vacuum. Each thread is a whisper of momentum. Each whisper multiplied by millions of seconds nudges a traveller across a landscape of gravity that would otherwise be perfectly predictable. This is why astronomers annotate interstellar visitors with small non-gravitational terms without blinking. They are not granting the object agency. They are granting the sun warmth, ice, softness, rotation, complexity, the entire small physics of a breathing stone. So when you hear that 3I Atlas exhibits non-gravitational acceleration, hold the phrase lightly. It does not mean trickery. It means sunlight and shadow taking turns. It means thermodynamics writing in the margins of Kepler's ellipses. It means that in a universe ruled by gravity, even a breath can matter if you give it time. And time is the one thing interstellar travelers always have. High above the air that blurs and bends starlight, two eyes of humanity turn toward a single point, one golden, one blue. The Hubble Space Telescope. Earth's restless sentinel circles our planet every 97 minutes, peering in visible light, the same kind your eyes see, only sharper, steadier above the atmosphere's trembling breath. And farther out, still 1.5 million kilometers from home, in the quiet shade of the L2 point, the James Webb Space Telescope waits in cold silence, its golden mirrors open like petals. Together they watched 3I Atlas, one seeing its reflection, the other feeling its warmth. The partnership was poetic sunlight and heat, blue and gold, two complementary ways of hearing the same faint whisper from another star. From Hubble's perspective, the task seemed impossible at first. The comet was dimmer than a 19th magnitude star, a grain of dust against infinity. Every photon took minutes to arrive, every image smeared by its own motion across the background stars. Astronomers worked patiently, taking dozens, then hundreds of exposures each, only a faint exhale of light. The raw frames were nearly empty, haunted by noise and cosmic rays. But the trick as always lay in patience. They aligned each exposure on the comet's predicted motion, not the stars, then stacked them, letting the signal add and the randomness cancel. Slowly the noise faded, a smudge sharpened, a faint tail emerged, bending ever so slightly away from the sun. What had been an invisible wanderer became something with shape, brightness, and motion, the beginning of identity. Hubble's blue eye works by reflection. It catches sunlight scattered from the dust and ice grains that surround the nucleus. The reflected spectrum is biased toward the shorter wavelengths, ultraviolet, and visible, giving insight into dust-sized color and composition. Tiny grains scatter blue light more efficiently. Larger ones glow warmer, redder. By measuring how the brightness changes across filters, scientists can infer whether a comet's halo is fine powder or coarse grit. 3I Atlas's light leaned toward the neutral grey particles larger than a micron, carbon-rich, non-icy. It was one more hint that this wasn't the watery kind of comet our system breeds. Yet Hubble, for all its brilliance, can only see what sunlight reveals. It cannot sense the heat of molecules, the infrared fingerprints of ices that radiate in darkness. That is where Webb's golden eye awoke. In the deep infrared, its instruments can see the world. That light leaves behind the faint glow of warmth escaping from the comet's coma, the molecular vibrations of carbon monoxide, dioxide, methane, and dust. Where Hubble sees color, Webb sees chemistry. To Webb's instruments, 3I Atlas wasn't bright. It was a ghost barely warmer than background space. But Webb's mirrors, each hexagonal and plated in gold to reflect infrared light, efficiently gathered those whispers of heat and spread them into spectra. In those spectra lay revelation. Instead of the dominant signature of water vapor that defines most comets, Webb recorded strong lines from CO and CO2 and only traces of H2O. It was confirmation of what Hubble had hinted, a chemistry born in deeper cold under a weaker sun than ours. Each element of data-like curved tail spectrum reinforced the same story. 3I Atlas came from somewhere else, a star whose nursery froze different gases first. Even so, this information didn't arrive as a photograph. It arrived as numbers, columns of wavelengths, intensities, noise levels, a spreadsheet of starlight. Teams of astronomers spent months cleaning, calibrating, subtracting backgrounds, correcting for instrument temperature. A single misflagged pixel could mimic a signal. Every curve had to be rechecked. This was science at its quietest, hundreds of hours of software and skepticism before a headline could be written. Out of terabytes of raw data, a few kilobytes of truth emerged. Stacking and filtering those are the metaphors of astronomy, but also of understanding. Each exposure by itself shows almost nothing. Only by combining them do patterns appear. It's a reminder that reality is cumulative. Patience is how you turn noise into knowledge. The dual view was essential. Hubble's blue eye traced how sunlight bounced off the dust the comet's visible costume. Webb's golden eye traced how heat seeped from the molecules the comet's inner voice. Put them together, and you get something close to personality, an object of another star revealed not by shape alone, but by temperament. Cold, carbon-rich, reserved, yet quietly active. For the astronomers awake through those long nights, the data stream was almost emotional. Each successful exposure, each line of spectrum felt like a message delivered across eons. They knew the photons falling on their detectors had left 3I Atlas hours earlier, having travelled hundreds of millions of kilometres. They had been reflected or emitted by matter that once circled another sun in a system that may no longer exist. Now those same photons were painting the sensors of two human-made eyes, separated by 1,000,000 miles collaboration on a cosmic scale. The universe, they realized, is not silent, it's just quiet. It speaks in wavelengths and waits for patience. Between the blue eye and the golden one, we learned to listen. And when the images were finally processed, Hubble's visible smudge superimposed on Webb's thermal glow, the composite showed something simple yet profound. A pale thread of dust, a faint halo of heat, an object smaller than a mountain, but older than history. No flare of engines, no alien geometry, no secret signals, only the delicate interplay of sunlight and ice. Energy and entropy captured by two telescopes that in their union made the universe a little less dark. Every mystery in science begins not with the impossible, but with the slightly odd. 3I Atlas was odd in exactly that way. Not a miracle, not a contradiction, just a handful of details that refused to line up neatly with precedent. Each anomaly taken alone had a natural explanation, but together they hummed with tension like notes that belong to different chords yet resonate in the same air. That resonance is where curiosity begins and where speculation finds its foothold. Start with the chemistry. Hubble's blue eye saw muted water lines. Webb's golden instruments confirmed it water vapor. The signature breath of every normal comet was faint, almost reluctant. Instead, carbon-bearing gases dominated CO and CO2 in abundances far higher than those found in comets of our own solar system. It's not impossible. CO freezes at temperatures much lower than water, so a comet born in a colder region would naturally retain more of it. Yet the ratios were extreme, the balance inverted. This chemistry painted a picture of a birthplace on the outskirts of some distant star in perpetual winter, so far from its sun that water never condensed in the first place. The spectrum looked alien, not because it broke physics, but because it followed another star's rules. To the cautious, that meant diversity. To the speculative, that meant design. Next came the geometry. The anti-tail, that phantom streak seemingly reaching toward the sun, wasn't defiance of physics, but a trick of alignment, a perspective illusion produced by the Earth crossing the comet's dust plane. Still, the optics of it unsettled people. The image of a two-tailed visitor, one pointing away, one pointing toward evoked symmetry, and symmetry in space feels intentional. Human instinct reads balance as architecture, even when it's just the byproduct of orbits and sunlight. The photograph travelled faster than the explanation. Headlines spoke of comet with reverse tail before a single peer-reviewed paper clarified the view. Then came shape and motion, the light curves whisper of elongation and tumble. Not a neat spin, but a slow, uneven roll, suggesting an irregular, perhaps flattened form. Oumuamua had done this to flashing brightness tenfold as it tumbled its cigar-like body, reflecting sunlight in rhythmic bursts. 3i Atlas's flicker was gentler but similar, a steady seesaw in luminosity. Rotation period roughly 12 hours, shape ratio maybe 2:1 or more. That was enough to awaken the same half-memory of 2017 when a Harvard astrophysicist dared to ask whether such shapes could be engineered, light sails shards, fragments of something thin. The resemblance didn't prove anything, but pattern recognition is a powerful drug. Individually, none of these traits crossed the threshold from unusual to impossible. Low water content, we've seen that in distant cold-born comets. Anti-tail, a geometric effect known since the 1950s. Elongated rotation, common among small fragments. But combine them, add the interstellar origin, the unfamiliar chemistry, the double tail, the asymmetric light, and you get something that feels scripted. And feeling, though not evidence, is often where fascination begins. Scientists recognize this dance intimately. They live in the grey zone between anomaly and explanation. Anomalies are the yeast of progress too many and the bread collapses. Too few and it never rises. So they tread carefully, aware of the magnetic pull of mystery. When something looks like a pattern, the responsible move is not to dismiss it, but to test it to measure where it diverges from ordinary behaviour. In the case of 3i Atlas, those measurements returned ordinary numbers hiding in extraordinary context. The non-gravitational acceleration matched sublimation models. The spectra matched chemistry possible under extreme cold. The geometry matched perspective effects well known to dynamicists. Each oddity, once isolated, behaved normally. But isolation isn't how humans experience wonder, because wonder is combinatorial. We don't marvel at a single data point, we marvel when many align imperfectly like stars forming a face in the dark. And 3i Atlas gave us that face, a cold-born, carbon-rich, oddly spinning visitor, whose image looked both natural and composed. Enough to stir the imagination, not enough to satisfy it. That gap between evidence and possibility is precisely where stories breed. Avi Loeb understood that gap well. When he spoke of a 10% chance that 3i Atlas might be artificial, he wasn't presenting a number derived from equations. He was quantifying the itch of uncertainty. 10% was shorthand for we can't fully rule it out. To the public that sounded thrilling. To scientists it sounded reckless. But both reactions sprang from the same source, the simple fact that the comet didn't behave quite like the ones we know. And yet science's job isn't to eliminate oddness, it's to understand it. Every confirmed anomaly eventually finds its family. Pluto's orbit once seemed bizarre until we learned about resonance. Mercury's precession seemed supernatural until relativity. The trick is patience, letting the strangeness breathe until data outgrows rumour. So what makes 3i Atlas feel odd? Not any single fact, but the way facts conspire to provoke intuition. It's the soft mismatch between expectation and observation, a pattern we can't unsee even when logic tells us it's fine. It's the feeling of standing before a locked door whose key you almost recognise. The door may open to nothing more exotic than frozen gas, but until it opens, the imagination peers through the keyhole and sees civilizations. That's the paradox of discovery. The same anomalies that tempt us toward fantasy are the ones that lead us to truth. If we're disciplined, they become evidence. If we're impatient, they become myth. And in the case of 3i Atlas, the distinction lies not in the sky, but in ourselves, in our longing to find meaning in every flicker, tail and tilt of light. Science at its heart is an exercise in humility. It doesn't deny wonder, it just insists that wonder earn its evidence. And for every extraordinary claim, the bar rises accordingly. Carl Sagan phrased it perfectly: extraordinary claims require extraordinary evidence. It isn't cynicism, it's calibration, a safeguard that keeps our telescopes aimed at truth rather than at dreams that glare too brightly. With 3i Atlas, the early whispers, alien sail, engineered fragment, deliberate messenger came long before the data was complete. But when the numbers settled, a quieter consensus emerged. Not dismissal, but context. Each anomaly that seemed to hint at artifice found a precedent, a cousin, a mirror within the vast messy family of comets we already know. Take the missing water. At first it looked scandalous, a comet without the very ingredient that defines comets. But the solar system has produced plenty of such creatures before. In 2018, astronomers studying comet C 2002 V494 for Linear found it dominated by CO and CO2 with barely a trace of H2O. Comet 29P Schwarzmann-Wachmann 1, a peculiar body orbiting between Jupiter and Saturn, also vents mostly carbon monoxide. Even within our own backyard, volatile chemistry can differ wildly depending on where a comet formed. Those born in colder regions preserve more CO ice because it condenses at lower temperatures. Those formed nearer the Sun lose it early and end up water-rich instead. Seen through that lens, 3I Atlas is not unthinkable, just foreign forged under another star's cold rulebook. Its chemistry doesn't defy nature, it extends it. Now the anti-tail the wrong way plume that lit up message boards and tabloids alike. Astronomers have documented this illusion for decades. The famous comet Rn-Roland in 1957 showed it vividly, sparking a wave of public fascination and confusion long before Photoshop or clickbait existed. Its sunward streak turned out to be a sheet of dust seen edge-on illuminated just so by our changing viewpoint. Comet Pan-STARRS in 2013 did it again. The geometry is simple, the effect dramatic a trick of perspective that transforms a flat plane of particles into a celestial paradox. 3I Atlas merely joins that lineage, performing the same optical magic across interstellar miles. As for the elongated tumbling rotation, it's tempting to read intention into symmetry or rhythm, but a symmetry in the cosmos is the rule. Oumuamua's extreme light curve made headlines for its tenfold brightness swings, yet within our own solar system comet fragments show similar eccentricities. After Comet Shoemaker-Levy 9 broke apart in 1992, its shards displayed wild spin rates and irregular shapes. The nucleus of Comet 67P Churyumov-Gerasimenko, mapped by the Rosetta spacecraft, looks like a rubber duck, two lobes fused in a slow-motion collision. Such odd geometries are not engineered. They're sculpted by billions of years of gentle violence impacts tidal stresses thermal cracking. 3 Atlas's flickering light fits comfortably in that gallery of imperfections. Even the non-gravitational acceleration, so quick to be labelled thrust or steering, finds endless company in the cometary record. When 1P Halley approached the Sun in 1986, its orbit shifted by measurable amounts from the jets of outgassing vapour. NASA's Deep Impact Probe observed similar nudges on Tempel 1 in 2005, millimetre-per-second accelerations accumulating into kilometres of drift. Nothing supernatural, just the persistence of physics. 3I Atlas, small and volatile, would naturally show the same behaviour, only magnified by its reduced mass. Even its brightness irregularities, those heartbeat fluctuations in the light curve, have analogues. Comet 2P Encke, one of the shortest period comets known, brightens and dims erratically because of uneven albedo in rotation. So does Comet 9P Tempel, so did Hyakutake, and so will the next one that wanders too close to the Sun. In every case, the pattern traces back not to artifice but to topography. Cliffs, vents, shadows, and the simple fact that roughness is the universe's favourite shape. Put these pieces together, and the mosaic clarifies. 3 Atlas may be unusual in combination, but not in kind. It's the first interstellar example that behaves like the strangest of our local ones. It doesn't rewrite physics, it simply broadens the sample size. This is the quiet triumph of scientific reasoning. The moment you recognise that an anomaly has cousins, it ceases to be a crisis and becomes a clue. Every odd comet expands our sense of what normal can include. That doesn't make the object less extraordinary. It makes the cosmos more so a reminder that our definitions were too narrow, our examples too provincial. And yet the consensus never dulls the awe. Scientists know that explaining a phenomenon doesn't exile wonder, it invites it to evolve. Each precedent is a story of discovery, of patient data gathering that replaced myth with mechanism without stealing the beauty. When 3I Atlas loses its halo of speculation, what remains is even more astonishing, a half-kilometre shard from another sun, carrying a chemistry written in alien ratios, moving at 60 kilometers per second, passing through our neighbourhood, once in 100 million years. That's the irony the headlines missed. The truth, natural, ordinary in law, but extraordinary in circumstance, was better than the rumour, because it means we live in a galaxy where fragments of other worlds find us silently, randomly, and without intent. The extraordinary is not the exception, it's the background hum of reality. All we need is the patience to listen carefully enough to tell which kind of extraordinary we're hearing. It starts the way it always does, with a whisper that sounds more like a headline than a hypothesis. A faint object appears in a survey feed, a handful of telescopes collect a handful of frames, an orbit fit emerges with wide uncertainty bars. Before those bars have time to shrink, a narrative steps in to fill the space. It's steering, it's pulsing a signal. NASA is hiding the real data. You've seen this movie. The plot never changes. Only the protagonist does. The first rumour is almost always agency. If a comet deviates a hair from a pure gravitational path, the word steering appears as if the object had hands. In reality, the effect is tedious, and terrestrial sunlight warms volatile ices. The ices sublimate. The escaping gas produces a small thrust. We measure that thrust in millimeters per second. It's not a wheel turning, it's a tea kettle. But on social platforms, millimeters do not trend. Steering does. The second rumour is signal. A light curve, the ordinary rise and fall of brightness as an irregular body tumbles becomes pulses. A graph with a repeating wiggle is halfway to Morse code in the human brain. And yes, the wiggle repeats. Rotation tends to do that. But real signals carry structure that survives scrutiny-consistent phase, under changed geometries, narrow band features, coherent modulation out of proportion to simple reflection. What astrophysicists find instead is a messier music amplitude that shifts with viewing angle phase that slips as active vents turn on and off harmonics that come and go with dust. A lighthouse it is not. A rock absolutely. The third rumour is secrecy. NASA is hiding. The truth is an engine that never runs out of fuel. It thrives on the assumption that the sky is proprietary, but the sky is not proprietary. The reality is boring in the way that makes truth durable. Positions, magnitudes and orbit solutions are posted openly and daily. The Minor Planet Center aggregates astrometry from observatories around the world. Anyone can see the time-stamped measurements and who reported them. Ephemerides are generated by public tools. An amateur with a backyard setup and a modest CCD can point where the ephemeris says and watch the same smudge slide across the pixels. If a trajectory suddenly swerved, the first people to notice would not be a secret committee, but night owls in Spain, Chile, Arizona, Australia, and a dozen university domes under cloudless skies all arguing about it in the open. Conspiracies have a hard time surviving field tests that can be repeated by teenagers with telescopes. The reason myths outrun measurements is pace. Science is slow by design. Rumour is fast by metabolism. A photometry pipeline that takes days to clean calibrate and cross-check will always lose to a 20-second clip that says "look, it blinked." A referee who asks for one more night of spectra is heroic to colleagues and invisible to timelines. By the time a careful paper appears with an appendix full of error bars, 1,000 microvideos have set their narrative in concrete. We end up in a familiar asymmetry. The correction is dull, the claim is dazzling. But repetition is a kind of antidote. Here is what open data looks like in practice. A survey telescope flags a moving source and posts its candidate tracklets. Other facilities, professional and amateur, submit follow-up astrometry, right ascension, declination, timestamps, uncertainties. Software ingests those points and solves for an orbit. The solution is posted with uncertainties, not absolutes. As new nights roll in, the orbit tightens, the predicted positions gain precision. Photometrists share calibrated brightness measurements with filters attached. Spectroscopists post preliminary line identifications. Nothing glamorous, everything reproducible. If you want to check a claim, you don't ask permission. You download the same files and run your own fit. Because the pipeline is transparent, the viral simplifications can be tested in daylight. Claim, it changed direction overnight. Test. Compare the sky plane residuals observed minus computed positions for multiple nights. If the residuals grow smoothly and are explained by a standard outgassing model, you're seeing thermophysics, not a driver. If they jump discontinuously, you look harder at the astrometry at tracking rates at a bad centroid thrown off by a background star. Most of the time, the jump evaporates under beta reduction. Claim, the light pulses are evenly spaced, so it's a beacon. Test, fold the light curve over trial periods and examine how the phase coherence holds as Earth-Comet-Sun geometry changes. Real beacons keep their phase. Tumbling shards drift as the viewing angle and active jets modulate the brightness. The latter is what we keep seeing. Claim they're hiding the spectrum. Test walk to the preprint servers and instrument archives. Raw and reduced data are credited to teams but available often with calibration files and reduction scripts. If anything, astronomers are guilty of the opposite sin, oversharing figures crowded with caveats that few non-specialists will read. There is an irony here. The same openness that allows anyone to verify a result also allows anyone to cherry-pick a moment that flatters a myth. A single noisy frame, a cosmic ray striking a pixel, a tracking hiccup can be screen captured and labelled maneuver. A saturation artifact can be framed as a flash. Context is the cure. Stack the frames, subtract the background. Watch the anomaly vanish into the average. You might ask why not simply ignore the rumours, because they affect more than mood. They warp priorities. Headlines that scream craft and siphon attention from the subtler, richer story that a natural fragment from another star is rare enough and glorious enough without needing a pilot. They also train the public to expect fireworks where there is fidelity to mistake caution for cowardice. If we want the next generation to love science, we need to show them its real strengths: patience, transparency, repeatability, the virtues that make truth cumulative instead of viral. The community has gotten better at answering fast without becoming glib. Observatories now share annotated images alongside raw frames explaining tracking rates and alignment showing what stacking does and why. Educators post side-by-side plots. Here is the pulse as a light curve. Here it is after phase folding. Here's why it's rotation. Dynamicists publish orbit fits with and without non-gravitational terms, so readers can see what steering looks like when the model ignores physics, and how it vanishes when you add sunlight and ice to the equations. This isn't spin, it's pedagogy, and it works slowly, but then so does everything that lasts. Meanwhile, the comet continues to be what it is. It does not care about our nouns. It sublimates it, sheds dust, it tumbles, it drifts a little off the path a gravity-only plot would sketch. Every night, telescopes capture more photons. Every morning, someone posts fresh numbers. And between those honest acts, myths lose a bit of their oxygen. There will always be a market for the sensational and a lag for the careful, but there is also a satisfaction no rumour can counterfeit the moment a messy dataset collapses into a clean curve. The night a predicted position lands its quarry in the centre of the CCD. The day an amateur's measurement in a backyard matches a professional's at a mountaintop. That is how you know the sky's telling you the truth when it agrees with itself in many hands. So let the cycle play out. Let steering trend for a day, pulsing for a week, hiding for a weekend. Then watch the plots march on night by night, indifferent and precise. In the long run, measurements outlast myths not because they shout louder, but because they add up. Rumours sprint, data accumulates. We live in a universe that rewards the latter. And for those willing to wait, the payoff is better than a conspiracy, a clear view of a real visitor, moving exactly as physics says it should, under a sun that hides nothing from anyone who cares to look. There is a quiet beauty to how astronomy keeps itself honest. Unlike politics or markets, the sky has no backroom. Every discovery from a supernova to an interstellar wanderer leaves its footprints in public code and timestamps. You can open them, plot them, argue with them, improve them. The cosmos, for all practical purposes, is open source. The clearinghouse for this transparency is the Minor Planet Center in Cambridge, Massachusetts, a nondescript office linked to the Smithsonian and the International Astronomical Union, but in practice the heartbeat of our celestial bookkeeping. Every night, telescopes across the world, robotic survey arrays in Hawaii amateurs in Arizona University domes in Italy, upload their raw coordinates for any moving object time of exposure, right ascension, declination, brightness, and the uncertainty in each. The MPC aggregates these and posts them online, sometimes within hours. Anyone can see the list of observers, the measurement counts, the residuals between prediction and reality. You don't need clearance, you need curiosity. That's the architecture of trust, nothing hidden, everything time-stamped. When 3i Atlas was first logged, the MPC designation appeared like a birth certificate, C2025, A1 Atlas, followed by lines of digits, the orbital elements, the epoch, the eccentricity greater than 1. Within a day, the provisional orbit was public, a few dozen astrometric points plotted from Hawaii to South Africa. Within a week, hundreds more arrived. Each observatory added its small brick of certainty, shrinking the error ellipse around a moving dot until its trajectory could be projected months ahead. By then, the object's hyperbolic path was undeniable, and because those coordinates were public, anyone from NASA analyst to a high school club could verify it independently. This is what most conspiracy theories miss. Secrecy in astronomy is mathematically impossible. A genuine course change, even by a few arc-seconds, would ripple instantly through the data stream. If 3i Atlas suddenly steered its predicted position on the next night, would miss by enough pixels to catch attention from dozens of observers. The residuals would not agree. Orbit fits from different teams would diverge. Forums like Cloudy Nights and Astrobin would light up overnight. Did you see the offset? I rechecked the stack. Not there. It's the wind in your dome, not aliens. This is how rumours die in real time, not through censorship, but through math. Every line of data on the MPC is traceable back to a human being, or sometimes to a backyard robot guided by one. The human stories behind those lines are what make the open model so resilient. Take the amateurs retirees in Spain with 14-inch Newtonians teenagers in Chile, aligning their CCD's software developers in Poland, who wrote their own astrometry scripts for fun. They don't wait for permission to contribute. They track, stack and upload often, with precision rivaling professional observatories. Some use remote access to telescopes in Australia chasing the Comet, while their own hemisphere sleeps. They're not fringe hobbyists, they're co-authors of reality. Astronomy has always relied on this democratic backbone. When a near-Earth asteroid sweeps by, amateurs confirm its path within hours. When a supernova explodes in another galaxy, it's often a small-town observer who spots it first. The sky is too big, the data too plentiful for any single institution to guard. Instead, it runs on a kind of distributed faith. Every photon that hits a detector can be verified by another somewhere else on Earth. It's peer review written across the planet's night side. That system is the reason we know 3i Atlas is real, moving exactly as predicted. Its position tonight is calculable to within a few arc seconds, a precision earned not by secrecy, but by participation. Every observation that matches the ephemeris reaffirms the orbit. Every new frame stitched into the archive tightens the story. The object doesn't hide, it leaves breadcrumbs of light anyone can follow. This openness does something profound to our relationship with the cosmos. It turns the act of discovery from a spectator event into a commons. No one owns the sky, we co-author it line by line. The data pipelines may be digital, but the spirit is ancient sailors charting stars, farmers, noting seasons, poets timing the moon. When a retired engineer uploads astrometry from his rooftop, he joins the same lineage as Galileo sketching Jupiter's moons. The medium changed, the ethos didn't. That democratization also disciplines the professionals. Knowing that amateurs are watching keeps the process honest. Every claim must survive replication. Every extraordinary headline must reconcile with the nightly grind of measurement. It's a self-healing system. When rumor says it moved, observation says show me. And showing is easy because the data is public. There's something beautiful about that. While conspiracy videos demand belief, the night sky offers verification. You can point your telescope to the coordinates and see for yourself. The photons arriving at your detector are the same ones that touched Hubble's mirrors and Webb's gold plates. They don't care who's collecting them. They only care that someone is paying attention. So when you hear NASA is hiding the truth, remember that NASA doesn't own the truth, the universe does. And the universe is remarkably bad at keeping secrets. Every comet, every supernova, every interstellar visitor betrays itself in photons that fall freely to anyone willing to look up. That's why 3i Atlas can never be a private mystery. It's a public event written across the heavens in real time, audited by thousands of eyes. In the end, this openness is not just good science, it's good philosophy. It reminds us that discovery belongs to everyone, that curiosity scales better than control, and that even in an era of algorithms and misinformation, truth still leaves a traceable trail of light. If you want to find it, you don't need credentials. You just need clear skies, a clock, and the patience to join the chorus of quiet observers who keep the universe honest. That's what the open source cosmos means, a sky that writes its own code in photons, a community that debugs it one observation at a time, and a world where even a single backyard telescope can help tell the story of a visitor from another star. Long before 3 Atlas crossed our sky, before Earth had continents or eyes to witness it, it belonged to another star. Not just as a traveller through its light, but as a fragment of its genesis, born in the cold outskirts of a swirling disk where dust and frost were still deciding which molecules to keep and which to lose. Every comet is a fossil from a birthplace like that, a time capsule of temperature and distance. Its chemistry is the diary of its nursery. And 3i Atlas, faint and fleeting though it is, carries in its vapours a fingerprint from another star. To understand that fingerprint, you have to picture the first few million years of a solar system's life. A newborn star sits at the centre of a rotating disk of gas and dust, what astronomers call a protoplanetary disk. Inside that disk, the temperature drops dramatically, with distance thousands of degrees near the centre, barely a few dozen in the outer reaches. This thermal gradient divides the elements like a cosmic vineyard, each region fermenting its own flavour of ice. Close to the star water, vapour can't condense. The heat keeps it gaseous, leaving only rock and metal grains to build the inner planets. Farther out, where temperatures fall below about 170 Kelvin, the water ice line appears a boundary beyond which water freezes and adds its mass to forming worlds. Still farther below 70 Kelvin carbon dioxide begins to freeze, and in the outermost reaches colder than 25 Kelvin even carbon monoxide solidifies. Each boundary acts like a shelf in a galactic pantry, storing different ingredients at different distances. When a comet forms, it inherits the chemistry of its shelf. A body assembled near the CO2 line will have a balance of water and dry ice. One born beyond the CO line will be rich in carbon monoxide but poor in water. The ratios of these ices water CO2 CO are like ratios in a vintage wine. They depend on the soil and the season of their making, the temperature, the pressure, the radiation, and the local alchemy of dust and starlight. Every star's disk leaves a different bouquet. Our solar system tends toward water richness. We live in a mild vineyard. But the spectra of 3I Atlas revealed a very different blend, almost no water-abundant CO and CO2, a recipe from a colder cellar far from its sun's warmth. That imbalance tells us about more than chemistry. It tells us about climate. If you rewound the comet's life to its origin, you'd find it orbiting a star smaller or dimmer than ours, or perhaps forming farther out in a wider disk. The abundance of carbon monoxide implies a region colder than any zone where our own comets gestated. Such environments exist in the outskirts of red dwarf systems, in the shadowed rims of binary disks in the perpetual twilight of stellar nurseries. Their molecules that would sublimate here remain stable, layering themselves onto grains of dust, locking away their chill. When those grains collided and clumped, they became planetesimal seeds of planets, moons, and comets. Some stayed loyal to their star. Others, perturbed by giant planets or passing siblings, were flung outward, exiled into the long night between suns. 3I Atlas was one of those exiles, a shard of a forgotten winter drifting for eons, until our gravity caught its passing glance. Astronomers sometimes call this kind of chemical heritage a cometary isotopic signature, a mix of ratios so distinctive that if we could line up all comets from across the galaxy, we could tell which system each one came from. Hydrogen to deuterium ratios, for instance, vary with temperature. The colder the birthplace, the more deuterium ends up in the water ice. Even within our own solar system, comets from different regions carry noticeably different isotopic flavors. Imagine extending that diversity across 1,000 stars. 3I Atlas is one of the first drops from that cosmic tasting, a sip of another world. The metaphor holds because spectroscopy is a kind of tasting a palette of wavelengths. When Webb's instruments split the comet's infrared light, they produced not a picture but a pattern, peaks where molecules absorb or emit, troughs where they remain silent. Those peaks are recipes written in light. From their heights and shapes, chemists can infer composition, temperature, even particle size. When scientists compared 3I Atlas's pattern to known comets, the differences were unmistakable. Where others sang water's familiar note at 2.7 microns, this one hummed low faint. Where carbon monoxide lines at 4.7 microns are usually background whispers, here they rang like bells. It was a spectrum from a different vineyard, entirely crisp, carbon-rich, frostbitten. If you wanted to falsify the idea that 3I Atlas is natural, this chemistry would be a terrible place to start. It fits beautifully within physics, elegantly within astrochemistry. There's no signature of smelting, no trace of metals, no engineered isotopic ratios, just the equilibrium products of a cold disk that froze in another pattern. Yet ironically, that difference is what makes it feel alien in the most poetic sense, not built by intelligence, but born under another sun. To look at it is to glimpse diversity on a galactic scale, proof that our way of building worlds is just one variation among countless others. The idea that every star system brews its own molecular flavor has profound consequences. It means the building blocks of life, the inventories of ices and organics, are not identical everywhere. Some worlds may begin rich in carbon, others starved of it. Some may flood with water, others with methane or ammonia. If life exists elsewhere, it will taste different, smell different, evolve under different recipes. And comets like 3I Atlas are our first imports from those cosmic kitchens. They're not just wanderers, they're samples, small reluctant ambassadors from stellar neighborhoods we will never visit. The beauty of science is that it can extract entire histories from a few photons. We can't reach 3i Atlas, can't touch its nucleus, or scoop its dust, but by reading its spectrum we can reconstruct the climate of its birth millions of years and trillions of kilometers away. It's as though the universe left us a label on the bottle: origin outer disk, low temperature, high carbon monoxide content. Vintage unknown system early epoch, best served cold. So when you hear that 3i Atlas is ordinary, remember what that really means. It's ordinary only by the standards of physics, not of wonder. It's a cosmic fingerprint pressed into our instruments, proof that other stars have their own vineyards, their own weather, their own stories. We may never know which star birthed it, but in studying its chemistry we've already shaken hands across light years. In the faint gas trailing behind it, the galaxy is introducing itself. When we speak of life between the stars, we don't have to imagine spores crossing light years or spacecraft bearing DNA. The humbler and far more likely picture is this dust and ice drifting, comets' fragments and frozen grains wandering through the dark carrying chemistry rather than creatures. This is panspermia's quieter cousin, not life in transit but potential in transit. And it begins in places like 3i Atlas. Inside every comet, even one from another star chemistry never sleeps. Its ice is water, carbon monoxide, carbon dioxide, methanol, ammonia are cosmic solvents waiting for energy. Cosmic rays, ultraviolet light, and the gentle warmth of nearby stars act as catalysts driving reactions that knit simple molecules into complex organics. Over thousands of years, those reactions can form amino acids like glycine, alanine and serine, nucleobases like adenine and uracil, and simple sugars that could seed further complexity once mixed with liquid water. Laboratory simulations have confirmed it again and again. Bake cometary ice analogues under ultraviolet radiation, and you get the building blocks of biochemistry. No miracle, just persistence. The Rosetta mission to Comet 67P Churyumov-Gerasimenko found glycine directly in its vapor. NASA's stardust samples from Comet Wild 2 contain the same. Meteorites that once belonged to asteroidal bodies have delivered over 80 varieties of amino acids to Earth. These discoveries paint a simple but radical picture: the universe is preloaded with organic ingredients. The recipe for life doesn't start on planets. It starts in the interstellar medium written on ice grains scattered by stars, baked by radiation, and stored in comets until chance delivers them to a waiting ocean. Now imagine multiplying that process by trillions. Every planetary system that ever formed has flung debris into interstellar space. Stray comets ejected by gravitational encounters, shards from planetary collisions, crust, fragments chipped off by impacts. Astronomers estimate that between the stars drift perhaps a quadrillion interstellar objects the size of comets or larger. The galaxy is not empty. It is a slow-motion snowstorm of chemistry. Each traveller, like 3i Atlas, carries its native molecular blend, some richer in hydrocarbons, others laced with nitrogen or sulfur. Together they form a galactic exchange network, a migration of ingredients that has been going on since the first planets cooled. It doesn't require directed purpose. Gravity and chaos do the work. A passing star perturbs a planetary cloud, ejects thousands of comets. Some wander for millions of years before grazing another system's outskirts, where a few are captured, vaporized, or smashed into young worlds. Each impact delivers a tiny starter kit, frozen organics, reactive clays, and the carbon backbone of future cells. Most will burn up, some will persist, and a fraction will seed chemistry that takes the next step. In that way, life need not have one birthplace. It could be a distributed experiment conducted unconsciously by the galaxy itself. To skeptics, the idea sounds romantic, but the math is surprisingly sober. Even if only 1 in a billion comets ever crosses from one system to another, and only 1 in a million impacts finds a world with liquid water over billions of years, the cumulative number becomes vast. Probability multiplied by time becomes inevitability. The cosmos is patient. It only needs a handful of successes. Panspermia in this modest form doesn't claim microbes sail through vacuum unharmed. It claims that chemistry travels and chemistry is enough. Because the first spark of biology is not the cell, but the molecule, the formation of chains capable of storing and copying information. Comets are not spacecraft, they're laboratories. Each one runs a million-year experiment in organic synthesis under conditions we can barely replicate. And when they die, when they sublimate near stars or crash onto moons, they scatter the products freely. In that scattering lies the possibility of connection, not lineage but kinship of matter. 3i Atlas then is a courier. Its lack of water doesn't make it less fertile. Its carbon richness makes it a better seed. Somewhere in its dust molecules more complex than any found in the primordial nebula may be waiting half-formed, preserved by cold. We may never capture them, but the idea that they exist, that they have already crossed the gulfs between suns, reshapes how we think about isolation. Stars are not sealed ecosystems, they leak. And what leaks are ingredients for worlds. From that perspective, our own story may have begun with a delivery like this. Billions of years ago, when Earth was still molten and bombarded, comets poured organics into its young oceans. They didn't bring life, they brought potential, the raw alphabet from which life could write itself. If interstellar wanderers like 3i Atlas have been passing through every few centuries for eons, then our planet has been collecting cosmic mail since before life began. We are the descendants not just of stardust, but of shared dust chemistry, traded among neighbours across spiral arms. It changes the definition of solitude. When you look up and see a comet, you're not watching an outsider. You're watching a conversation in the galaxy, speaking in molecules, exchanging recipes, scattering seeds. If even one of those seeds once landed in a young ocean and found the conditions right to self-assemble, then every breath you take is proof that the conversation worked. That's the quiet grandeur of the idea. Life may not be rare because it is miraculous, but because it is inevitable given enough time to spread. 3i Atlas is part of that long diffusion, a single grain in a wind that has been blowing for billions of years, carrying the scent of chemistry from star to star. And whether or not it ever touched a living world, it carries the same message as every comet that came before, that creation is not local, that the universe has been cross-pollinating itself since the dawn of time, and that in every passing fragment of ice and dust drifts the simplest truth imaginable: we are built from stories the galaxy never stopped telling. Distance in astronomy is rarely about space alone, it is about time disguised as space. You can measure how far something is by how old its light has become. Every telescope is a time machine, and every comet a messenger delayed by eternity. To feel what that means, you have to shrink and stretch the same idea until it hurts. Start small. The moon is roughly 384,000 kilometers away. Light covers that in 1.3 seconds less than the blink between heartbeats. An Apollo astronaut once joked that radio delays made lunar conversation feel like speaking through shyness. From our perspective, the moon is a neighbour you can call and expect an answer before your tea cools. Now move to the sun 8 light minutes. Everything we see of it, every shimmer and flare, is 8 minutes old. If the sun were to vanish this instant, it won't. We'd live those minutes in blissful ignorance before the darkness arrived. Even at that scale light, the fastest thing in the universe begins to seem slow. Jupiter, where 3i Atlas first appeared beyond, lies more than 40 light minutes away. By the time we saw the faint smudge of its approach, the photons announcing its presence were already 3/4 of an hour old. Every image of a planet is a photograph from the past. The sky is a museum, and the exhibits are still moving. But stretch further out to a light year. At light speed, 1 year is 9.46 trillion kilometers, a number so large that saying it aloud is meaningless. And 3i Atlas didn't come from 1 light year away. It came from somewhere tens, maybe hundreds of thousands of years distant in light travel time. Even if it drifted at 60 kilometers per second, astonishing by human standards, it would need millions of years to cross the gulf between stars. Think of that, an object the size of a mountain travelling faster than any probe humanity has built, still taking longer than our entire species' existence to complete a single voyage. That's the scale of motion the cosmos operates on. Fast becomes slow, short becomes infinite. What seems like speed to us is glacial to the galaxy. When astronomers calculate the paths of interstellar visitors, they aren't tracing trajectories through empty space. They're writing biographies through epochs. The comet's outbound path is older than civilization. Its inbound leg may have begun before mammals ruled Earth. By the time it leaves, humans will have changed again or gone. It doesn't orbit the sun, it passes through our story. Relativity in this context is not a formula, but a feeling. Einstein taught us that space and time are woven together. Here you can see the threads. Imagine a traveller aboard 3i Atlas, if such a thing could exist. For them, every moment of motion is ordinary, each second a second. But for us, their path spans eras. Between departure and arrival, whole continents drift, stars are born, languages rise and vanish. We live inside the time dilation of perspective, not velocity. The sheer difference in how long 1,000,000 years feels to a species that counts in days. Scientists sometimes say interstellar space is static. In truth, it's not still, it's slow. The particles move, the fields fluctuate, the stars orbit the galactic center once every 200 million years. To a comet, the galaxy's spiral arms are a breeze it barely feels. It drifts through gradients of radiation and gravity like a dandelion seed in an unseen current. 1,000,000 years for it might feel no different than a minute in a still pond. Time at that scale loses texture, and yet the comet's clock still ticks not in seconds, but in isotopes. Its ice remembers cosmic rays, recording them like tree rings. The ratio of argon to neon in its trapped gas tells how long it's been exposed. By studying that, scientists read the slow heartbeat of its journey. What we call timeless still accumulates history just at a tempo too slow for us to sense. To grasp that tempo, try this. If the Earth's age were compressed into a single year, then modern humans appear in the last half hour of December 31st. The Apollo missions occur in the final half second before midnight, and 3I Atlas. Its trip through the void would have begun back in early March when the planet itself was still a molten ball cooling in the sun's first spring. That's the kind of timescale we are borrowing our wonder from. In that light, the phrase different timelines is not metaphorical. Each celestial body carries its own chronology. Our seconds, hours, and years are provincial units, good for hearts and harvests useless for galaxies. When a comet like 3I Atlas arrives, it is literally from another era. The atoms in its ice have been asleep since before our biosphere formed. The star that cast it out may have changed, moved, or died. It may be the sole surviving witness to a world that no longer exists. So when we aim telescopes and catch its faint glow, we are not just seeing distance. We are seeing time in translation. Those photons left when mammoths still grazed Siberia. They carry the memory of an object that has been moving since long before our species learned to dream. And yet in this moment, this brief overlap of timelines, we share a night. For a few months, the speed of the cosmos and the brevity of human curiosity intersect. Then the comet will fade, taking with it a 1,000,000-year story that only brushed ours for an instant. That is what scale means out here. It's not a number to calculate, but a feeling to surrender to that vastness can coexist with intimacy, that a speck of dust can carry an epic that we are always living among ghosts of motion too long to follow. Every interstellar visitor is proof that time has geography, and every act of observation is a reunion across that geography, a handshake between moments millions of years apart. There's a quiet confession at the heart of every alien artifact headline. It isn't really about data or orbits or reflectance curves. It's about us, the animal that wants the sky to answer back. When people looked at 3I Atlas and whispered that it might be engineered, they weren't being irrational so much as human. We are built for agency detection, the evolutionary reflex that hears intention in the rustle of grass, sees faces in clouds, gods in thunder, and meaning in motion. For most of our history, that reflex kept us alive. Assuming the movement in the dark had a purpose was safer than assuming it didn't. Better to mistake wind for a predator than the other way around. Millennia later, telescopes have replaced spears, but the reflex hasn't changed. When something moves in unexpected ways, we look for the hand behind it. Then there's narrative hunger, the deeper current that runs beneath our curiosity. We don't like blank pages. Every culture, every myth, every scientific epoch has filled the cosmic silence with stories. The chariots of the gods, the canals of Mars, the radio pings of intelligence. The story of the universe is easier to hold when someone somewhere is telling it back. An interstellar comet that turns out to be just frozen gas feels like a letdown, an unopened letter, that after all the anticipation turns out to be junk mail. But that feeling says more about our emotional metabolism than about the cosmos. Our longing for neighbours is not naive, it's a symptom of empathy at scale. We want confirmation that thinking and feeling are not accidents of a single planet, that somewhere out there, another intelligence once looked at their own comet and wondered the same about us. Every time a rock from another star passes through our system, hope rides on it. Maybe this time it will blink, rotate, evenly broadcast a pattern. Maybe it will prove we're not alone. That hope doesn't die easily even when spectroscopy, astrometry, and every sober metric point to ice and dust. We still squint just in case. The irony is that in chasing the artificial, we sometimes overlook a subtler, deeper kind of wonder, the natural intelligence already written into the laws themselves, the physics that can sculpt a comet's orbit from chaos into elegance. The chemistry that without intention assembles the building blocks of life, the gravity that pulls one star's debris into another's light. There is artistry in that, but because it lacks authorship, we tend to miss it. We confuse silence for emptiness, order for intention. We want to shake a hand when the handshake has already happened in photons. Scientists feel this tension too. They live at the intersection of skepticism and yearning, trained to demand proof, yet wired to hope for revelation. That's why even Avi Loeb's 10% captured imagination, not because the odds were good, but because the desire was. The possibility, however remote, let us indulge for a moment in the dream that the universe might finally be personal, that we've been seen. But if we listen closely, 3i, Atlas, does speak, just not in a way that flatters us. Its message is not "you are not alone", it's "you are connected". It's the universe saying the same chemistry that builds you builds me. The same forces that hurl me across the void bind your world to its star. It reminds us that the cosmos doesn't need authorship to be meaningful. Meaning can emerge without intent beauty, without design connection, without conversation. There's also comfort in recognizing why we want more. Our species lives in a small, noisy moment between silences a few millennia of light and words in a universe 13.8 billion years deep. We crave companionship because we can imagine it. We tell stories about aliens not because we're certain they exist, but because imagining them softens the loneliness of the cosmic scale. Every rumor of a message, every glint in the sky becomes a Rorschach for our hope. Yet perhaps maturity as a civilization and as individuals lies in learning to love the mystery even when it doesn't look back, to see the same emotional gravity in a natural comet that we'd assign to a crafted probe, to let curiosity replace confirmation. When we do that, the cosmos expands again, not with proof of others, but with renewed wonder at what is. So why do we want it to be alien? Because we're storytellers adrift in silence, and the idea of company makes the silence bearable. Because agency comforts us more than accident. Because it's easier to love the universe when it feels like someone else is in it. But the quiet truth is that someone already is us standing on a small planet, eyes up hearts, projecting meaning into the dark. And maybe that's all the universe ever needed to speak. Science, for all its precision, is not a language of certainties. It is a grammar of bounds, what the data permit, what they exclude, and what remains undecided between. The beauty of a well-drawn conclusion lies not in its boldness, but in the contour of its humility. And 3i Atlas, like every faint, fast and faraway object, is a case study in what data can and cannot say. The first limit is resolution. Telescopes, no matter how magnificent, can only collect a finite number of photons. Every image of 3i Atlas that humanity has taken is at root a handful of photons caught in a bucket after travelling hundreds of millions of kilometres. Stack enough of them, and you can measure brightness, colour, shape, but never detail. The nucleus remains unresolved, a sub-pixel blur. You can tell it's elongated because its light fluctuates. You can tell it's active because its brightness exceeds that of a bare rock. But whether its shape is cigar pancake or lumpy sphere, you cannot yet say. The pixel is too large, the distance too vast. Next come noise and signal, a pair that dance inseparably. Every detector has dark current thermal noise, cosmic ray hits and statistical scatter. Each observation must subtract the sky's own glow, the faint ever-changing background of zodiacal dust and atmospheric emission. After the subtraction, a residue remains, and that residue is where the comet lives. Scientists speak of signal-to-noise ratio, but it's more honest to think of it as a negotiation. How much faith you place in the whisper left after the noise is tamed. The fainter the object, the longer the exposure, the higher the risk that noise begins to impersonate the thing you want to measure. That's why early claims, the light curve repeats perfectly, the tail shifts, abruptly must be treated as drafts, not verdicts. The first rule of the sky faint things lie until proven otherwise. Then there are model degeneracy situations where multiple explanations produce the same observation. An accelerating comet could be driven by outgassing by radiation pressure, or by errors in astrometry. All three can yield identical fits if you adjust the parameters just so. A brightness variation might mean an elongated body, a tumbling fragment, or simply jets of vapor, turning on and off as it spins. Spectral lines can overlap. A dip at 4.6 microns could belong to carbon monoxide or to a blend of other carbon species. The art of analysis is not in picking the prettiest story, but in testing which ones survive every constraint at once, and sometimes more than one does. Degeneracy is not failure. It's honesty about what the data allow. This is why scientists rarely say is. They say consistent with. It's a phrase outsiders sometimes mistake for evasion, but it's actually discipline. When astronomers write that 3 Atlas is consistent with a co-rich comet, they are marking the limits of inference. Given our models and within our errors, this explanation fits better than others, but not uniquely. It's a pledge to stay within the data's reach. There's also the issue of uncertainty propagation, how tiny measurement errors grow as you compute with them. A tenth of an arc-second in astrometry can shift an orbit prediction by thousands of kilometers after months of extrapolation. A 1% calibration drift in brightness can alter inferred size by tens of meters. When scientists report error bars, they're not confessions of weakness. They're the measure of integrity. Each bar is a fence against overconfidence. Without them, numbers become fiction wearing lab coats. Even instrumental perspective has limits. Hubble sees reflected sunlight sensitive to dust. JWST sees infrared sensitive to heat. Neither can touch the nucleus directly. A gap remains between observation and reality, a translation layer filled with models. Every piece of data passes through algorithms, assumptions about scattering angles, albedos emissivities. The conclusions that emerge are model-dependent by definition. That dependence is not corruption, it's the scaffolding of understanding. But like any scaffold, it obscures as much as it supports. The public often wants binaries natural or artificial, alive or inert, true or false. But science operates in gradients. Between 0 and 1 lies a landscape of probabilities, confidence intervals and Bayesian updates. In that sense, we don't know yet is not a pause in discovery. It is discovery in progress. Each new observation doesn't replace uncertainty, it reshapes it. Certainty is a moving horizon, not a destination. This restraint is not lack of imagination, it's respect for complexity. It's what separates hypothesis from myth. Where rumour rushes to fill gaps with intention, science leaves the gap open and studies its shape. That openness, the willingness to stay incomplete, is the mark of true curiosity. It acknowledges that the universe is richer than any single explanation we can sketch today. So what can the data say about 3 Atlas? That it is real, interstellar active and carbon-rich. That its motion obeys physics. That its anomalies fall within the spectrum of known comet behaviour. And what can it not say, whether it carries anything living? Whether its chemistry once served a world that is now gone? Whether we are witnessing mere debris or the echo of a civilization we will never meet? Those questions remain open not because scientists are blind to wonder, but because they are loyal to evidence. In the end, this loyalty is itself a form of reverence. It accepts that the universe doesn't owe us closure, only clues. And the discipline to honour those clues without overclaiming is what keeps science from becoming superstition in disguise. The astronomers watching through Atlas know this balance intimately. They measure, subtract, calibrate, correct. They know what their instruments can say, and they know where silence begins. That silence is not ignorance, it is the edge of the map. Beyond it lies the vast uncoloured region labelled here be wonder. If you could stand inside the control room of a great observatory on a winter night, you'd realise that science at its core is profoundly human. All those pristine numbers and clean plots that end up in journals are born in a room that smells faintly of burnt coffee and ozone, filled with people trying to stay awake while the universe pours data into their screens. For every elegant figure of a comet's trajectory, there are hands tired, calloused, sometimes trembling, guiding telescopes through fog, correcting for tracking errors, coaxing meaning out of photons that left another star before language existed. It begins before sunset. Technicians in parkas check dome motors and coolant lines. Someone calibrates the spectrograph, a ritual of twilight flats and bias frames. On a second monitor, a chat window fills with greetings from colleagues, half a planet away, clear skies here. Seeing's rough but workable. When night finally falls, they open the shutters and the first stars slip across the dome slit like sparks in slow motion. Inside the room dims to red light. Keyboard clicks replace conversation. Each exposure is another small wager that the sky will stay clear long enough for a whisper of data to cross the void and register as a few hundred electrons on a sensor. The human room around the telescope is not glamorous. It's quiet, recursive, repetitive. Someone watches focus drift another monitor's humidity. A third edits the observation log, timestamps coordinates exposure IDs. When the comet finally appears, it's not a cinematic flash, but a faint smear that the software must chase across the field. "Got it," someone says softly. The others lean in, sip from cold mugs and exhale. For a few minutes, that dim speck is the center of the universe. Behind the scenes, software pipelines hum, data packets flow from observatory servers to reduction scripts written by grad students months ago. Python code flattens images, subtracts bias masks, cosmic rays. Noise maps are generated, fluxes extracted, timestamps corrected for barocentric offsets. The 1,000 quiet calibrations that make a photon meaningful. Each line of code bears initials in the comments. AR fixed the dark subtraction. KY updated the wavelength calibration. LP added an exception for missing metadata. These are the brushstrokes in an invisible fresco, unseen but indispensable. Outside, the sky is mercilessly beautiful. While the monitors glow frost forms on railings, you can hear the slow groan of the dome tracking a sound like an old ship turning to follow its compass. Through the slit, the comet moves just another point, but one that no human has ever measured before. Every few minutes, someone steps out to check conditions. They look up at the same stars ancient farmers used to plant by and whisper a quiet superstition. Stay clear, just a little longer. Science has equations, but it also has prayers. Across the world, other observatories echo this rhythm. In Chile, Hawaii, Arizona, La Palma. The Canary Islands' night shift overlap like gears in a vast machine. While one hemisphere dozes, the other keeps watch. Data from telescopes separated by oceans flow into shared databases, where they merge seamlessly. The comet becomes a global conversation, a smudge of light passed hand to hand, night to night. No one owns it. Everyone participates in its unfolding. In the morning, the observers sign off and hand their raw frames to the day crew analysts, pipeline engineers, archivists. The glamour fades into spreadsheets. Someone checks the FITS headers for errors. Someone else renames files so automation won't fail. Coffee brews again. Plots appear, brightness curves, residuals, preliminary spectra. The first question is always the same: did we get enough signal? Usually the answer is almost. Science is built on almost refined into enoughs. The data travel further to colleagues at universities who never saw the night sky that produced them. They will clean, reweight and fit models, layering code on code until the comet's orbit and chemistry are disentangled. But those numbers still carry the fingerprints of their origin, the humidity that night, the wind, the brief cloud that passed mid-exposure. Every plotted point on the final graph is a story compressed, a person's attention, distilled into a dot. Sometimes between long integrations, conversation drifts toward philosophy. "What do you think it really is?" someone asks. Another shrugs. "We'll see what the spectra say." But underneath the professional reserve, there's a shared pulse of wonder. Everyone in that room, from the postdoc to the janitor emptying trash bins, knows they are touching something older than humanity. When the telescope slews, when the delta scroll, they are part of a centuries-long relay, one generation of eyes handing the night to the next. By dawn, fatigue sets in. The comet fades into the morning glow. The dome closes, motors whirring softly like a sigh. Inside, the observers save the last log entries, target acquired. Data quality good. Observing complete. They step outside into the pale air, blinking against sunlight, feeling that peculiar weight of having watched the universe while the rest of the world slept. Somewhere, a colleague on another continent will pick up their data tonight and continue the vigil. That's what the public never sees, that behind every discovery, every elegant plot in a paper, there are nights of exhaustion and quiet joy, a human constellation built from patience. Science doesn't happen in grand moments of revelation. It happens in the endurance of people who keep their eyes open when the world is dark, who measure, calibrate, and trust that meaning will emerge from noise. The telescope is only half the instrument. The other half is the community orbiting it. And in that room full of red light, tired laughter, and the steady hum of cooling fans, the universe becomes not just something we observe, but something we share. If the galaxy writes postcards, most of them blow past our door and vanish into the trees before we ever notice. Not because they aren't there, but because our porch light is small and the night is large. For every three-eye atlar we catch statistics, whisper that countless others have already slipped by, dim fast and unannounced while our instruments blinked, clouds rolled in, or the object crossed the daylit half of the sky. How many are there? No one knows precisely, but 2 detections in quick human succession, Oumuamua in 2017 and Borisov in 2019, already forced a revision. Interstellar debris is not rare, it's common. Take a back-of-the-envelope approach. If surveys sensitive to 20/21st magnitude scanning a fraction of the sky each clear night find one such object every few years, it implies a local number density that is non-negligible. Millions to billions of bodies moving through the inner, few astronomical units over geologic time. Scale that across the Milky Way and millions to billions becomes trillions upon trillions. The galaxy is a slow blizzard of unbound rubble, a migration of shards from planetary systems we'll never see. So why don't we see more? Because detection is a game with loaded dice. Interstellar visitors tend to be small hundreds of meters dark-coated in carbon dust and fast tens of kilometers per second. Each of those properties hurts our odds. Small means fewer photons, dark means even fewer. Fast means the trail smears across a CCD diluting the signal and fooling algorithms tuned for point-like sources. Add geometry, we favour objects approaching away from the sun's glare at modest phase angles. A visitor that plunges sunward from behind the solar glare could be spectacular and invisible until it's already gone. Catching a third 3 atlas matters, because 3 points define not just a line but the beginning of a distribution. With 1 detection you have a rumour, with 2 a hint, with 3 a first sketch of reality. Rates, sizes, brightnesses, approach directions, each new interstellar object lets us refine priors and update the shape of the unseen population. Perhaps Oumuamua-like shards are more common than Borisov-like comets. Perhaps carbon-rich water-poor chemistry dominates among the coldest disk exiles. Perhaps most arrivals thread the ecliptic from high inclinations, victims of ejection slingshots around giant planets long gone. Every perhaps becomes a number once you have enough postcards in hand. Survey reach is the lever. A wide-field telescope that can see 1 magnitude deeper doesn't just add a little. It opens a much larger volume of space because the range at which you can spot a dim object grows, and visible volume grows with the cube of that range. Improve your limiting magnitude by 2 and you might increase your searchable volume by a factor of 4-8 depending on other cuts. Refine your moving object pipeline to recover trail detections, and you reclaim a class of fast targets that used to slip through the net. Add cadence so that faint movers are seen on consecutive nights, and you convert maybes into orbits. Each software tweak is a new pair of glasses. This is where the era of synoptic sky surveys becomes more than a phrase. A dozen years ago, a headline-grabbing object often depended on luck, a survey pointing the right way at the right hour, a human eye that didn't dismiss a streak as a satellite. Today, networks of instruments, Atlas, Pan-STARRS, ZTF and others divide the sky like a quilt, each patch revisited on machine schedules, each candidate flagged by code that's been trained, tested and retrained to love faint moving smudges. The next leap comes from even wider mirrors and better software, deeper limiting magnitudes, faster reads, smarter subtraction of star fields and pipelines that expect interstellar kinematics instead of treating them as outliers. What does that mean in human terms? That one every few years begins to look eventually like several per year. Not because the galaxy changed, but because we did. We widened the door and turned up the porch light. We taught algorithms to notice trails that once looked like cosmic scratches. We learned to hand off suspicious detections from Hawaii to the Canaries to Chile in a single night, spinning the planet into a continuous telescope. Even then, most postcards will go unread. Consider the blind spots, daylight, half the sky is invisible every moment, an immovable limit that eats discoveries. Whether an object can cross our best survey footprint on the only cloudy week of a season. Glare, the sun's crown, hides a rich hunting ground where many visitors likely dive and depart. Bias our pipelines, no matter how clever, are tuned by what we've seen. The truly weird may be filtered out as artifact. Knowing these blind spots matters because it lets us design around them, plan twilight surveys, build space-based sentinels to stare near the sun archive, raw images so future algorithms can remine old skies for things we missed the first time. There's a philosophical angle too. Each new interstellar detection shrinks the role of luck and expands the role of expectation. Oumuamua felt like a miracle, Borisov like a pattern forming, Atlas like confirmation that we now live in a world where the background rate of alien rubble is unobservable. That shift changes budgets, observing proposals, even graduate theses. You can plan a project around a phenomenon you expect to see again. You can allocate time for rapid response spectroscopy without apologizing to committees about chasing a unicorn. The postcards metaphor helps here. Imagine standing on a bluff in a wind full of paper. At first, you catch one by accident, then another because you're alert. Soon you bring a net, then friends with bigger nets. Then you study the wind and learn the hours when the gusts are strongest and from which direction. You're no closer to the printing press that made the postcards, but you are suddenly rich in messages, place names, ink scents, scraps of handwriting that hint at distant cities. That's what interstellar objects are, incomplete messages that in aggregate sketch the contours of worlds we will never visit. This sobering truth is that even with perfect surveys we will still miss most of them. There are too many and they are too faint and space is too vast. But most is not all, and enough is the word science loves. Enough detections to build a size distribution. Enough spectra to map a chemistry atlas of other stars' nurseries. Enough light curves to learn how shards are shaped by ejection and erosion. Enough precise orbits to trace the kinematics of the galactic neighborhood to see which stellar streams send us more debris and which send us less. Catching a third visitor then is more than a headline. It's a calibration point. It tells us our nets are working, that our porches are brighter, that our software knows a postcard when it sees one. It also tells us to expect surprise. 3 is not many. 3 can still mislead. The next object may be water-rich or metal-bright or so dark it's practically a shadow. Preparation is not prediction, but it is readiness, and readiness is how accidents turn into measurements. There's a tenderness in this work that numbers can't capture. Every time a new interstellar tracklet appears on a public page, someone somewhere loses sleep in the best way, tuning a telescope, pleading with weather-squeezing signal from noise. They know that if they miss this one, the wind will carry 1,000 more, but also that this one is now and now is rare. That's the paradox of a universe full of messages, abundance writ in decades, scarcity felt in nights. We will keep missing postcards, but we will also keep catching them more each year than the last until the stack on the table is thick enough that patterns emerge without squinting. And when that happens, the galaxy's handwriting, its favoured inks and flourishes, its cold fonts and warm ones will stop being rumour and become a map. Not of destinations we can travel to, but of origins, the vineyards of chemistry, the climates of disks, the violences of ejection, all from smudges that almost got away. That's what catching a third means. It means we're finally learning to live in a sky that is busy to treat wonder as a dataset, and to read the mail the universe has been sending all along. Let's play the game straight. Suppose 3i Atlas were not a shard of ice and dust, but a machine. What fingerprints would engineering leave on a visitor crossing the inner solar system? Not poetry, now tests. If someone built it, certain clues would be hard to hide. First talking. Machines that explore tend to communicate. The cleanest test would be a coherent beacon radio or optical narrowband, unnaturally bright, in a hair-thin slice of spectrum with structure that survives every instrument and every night. Think millihertz, stability, a carrier with sidebands. Doppler drift matching the object's motion, maybe polarization that's fixed in the emitter's frame. In the optical, an intentional beacon might appear as a laser-line sub-nanometer-wide monochromatic, indifferent to the messy forest of molecular bands we expect from gas. SETI-style observers would look for non-astrophysical modulation, prime number pings repeating geometric sequences, wideband chirps that compress cleanly, nature burbles, engineering counts, second shapes that make light misbehave, natural surfaces scatter broadly, engineered ones often glint, a flat panel foil or mirror throws sunlight into a tight specular lobe. If the object spins regularly, those glints arrive like clockwork, a metronome of knife-edge flashes with colour ratios that track the solar spectrum, not dust reddening. Photometrists would see a BRDF bidirectional reflectance distribution function that's sharp and mirror-like, not the soft powdery scatter of coma grains. Polarimetry would help too. Polished metal produces distinct polarization angles and degrees. Dusty coma yields smoother phase angle-dependent curves, A geometrically regular body also shows up in stellar occultations when it passes in front of a star. The light curve drops and rises with straight edges and consistent chords, not the ragged signature of an asymmetric lump wrapped in haze. Third, thermal behavior that refuses to be geology. Engineer a craft and you control emissivity and thermal inertia. An isothermal sail, a radiator panel, a heat sink. These would make infrared brightness vary in ways that ignore the usual rules. Hot day side, cold night side. Warm jets near subsolar regions. Spectrally, you might see a flat featureless continuum consistent with treated surfaces, not the bumpy blend of silicates, organics and ices. The temperature could hold oddly steady, while heliocentric distance changes as if active thermal management were at work. Point a sensitive IR spectrograph and you'd ask, where are the molecular lines? If nothing glows like CO or CO2, but something still thrusts that's suspicious. Fourth, dynamics that don't scale with sunlight. Natural non-gravitational acceleration rises and falls with heating. It wobbles with rotation. It correlates with measured outgassing. Engineering can do constant thrust directionally coherent over many rotations indifferent to how close you are to the sun. In orbital fits, this shows up as a force that refuses to be tamed by standard sublimation laws. If the push keeps the same vector in inertial space while the nucleus tumbles, physics raises its hand who's steering fifth materials that don't belong. Spectroscopy is nosy. Even low signal-to-noise spectra can betray alloys' broad flat reflectance. Lack of vibrational features, coatings, unusual UV blue slopes, or emission from excited atoms in lines that don't match cometary chemistry. If someone used advanced dielectrics, you might catch peculiar polarization wavelength dependence. If someone used high-purity isotopes, precision measurements might show isotopic ratios that don't match any known astrochemical pathway. Nature meanders, industry standardizes, sixth radar and two-way tests. A true machine might present a radar cross-section too big for its size, flat plates light up, or even reply in curious ways. Send a coded radar chirp if a return comes back with non-geometric delays or embedded structure that's a headline. We've lost Arecibo, but experiments at Goldstone and future arrays still matter. Even a null result, constrained surfaces, icy dust balls are radar dim. Metallic geometry is not. Seventh, clockwork. Machines keep time. Natural objects tumble chaotically. Jets turn on and off with solar noon. Spin rates wander. Engineering prefers regularity. A light curve with millisecond stability over weeks. A rotation that holds phase through torques that should disturb it. Those are the kinds of "that's odd" that don't fade under reanalysis. That's the thought experiment. Now what do we have here? We have no beacon. Scans in radio and optical have not uncovered stable narrowband carriers or modulations that survive geometry changes. The brightness fluctuations of 3 Atlas fold into periods that drift with viewing angle, classic for a tumbling body and active vents. The pulses some clips touted flatten into ordinary rotation once you remove clouds trailing and detector systematics. No prime numbers in the noise, just noise. We have no mirror metronome. The photometry shows uneven, non-periodic glints consistent with facets and albedo patches, not a mirror's razor flashes. Polarimetry trends match dusty Comet degree of polarization, rising with phase angle color slopes aligned with carbon-rich grains. The coma itself, faint but present, destroys mirror-like behavior, dust dilutes specular signals. Occultation attempts yield partial fuzzy chords, haze around a small core, no straight-edge silhouettes. We have molecules. Infrared spectra carry CO and CO2 unmistakably with weak H2O, a cold disk recipe. Those are lines, not laser slivers, bands not engineered continua. If thrust were present, we'd expect it to track those volatiles. And indeed, the small orbital residuals collapse when you allow sunlight-driven sublimation, no stubborn geometry-independent push left over that demands engines. We have thermal sense that behaves like rock and ice. Temperatures vary with heliocentric distance. The coma's color temperatures while noisy sit where carbon-rich dust would. No isothermal panels, no isentropic weirdness. The spectral energy distribution shows features not the polished flatness of machined radiators. We have messy time, not clockwork. The light curve's amplitude changes with phase. Harmonics appear and disappear, good for a lumpy venting shard, bad for a flywheel-stable craft. If there's a design, it is the design of entropy. We have no radar tail and likely won't given range and size, but that absence is expected for a dusty meter to hundreds of meters core wrapped in a coma. A metallic plate at this distance would be a different story. It is not the story we see. Could there be clever camouflage, a machine that mimics a comet perfectly? Hypothetically, yes. But then the question mutates from science to fiction. At what point does an explanation that reproduces all natural observables cease to be useful? Science prefers the simplest hypothesis that explains the data with the fewest special pleadings. Right now, that's the cold comet model, CO2-rich ices, from a deep freeze nursery dust, making the colours jets, making the drifts geometry, making the anti-tail, and time making the tumble. Humility matters both ways. If tomorrow a telescope caught a laser line anchored in the object's rest frame, or a strictly periodic glint with a specular BRDF, or a force vector that refused to scale with sunlight or spin, the community would pivot from interesting comet to instrument, every band phone, every dish. We have the checklist. We are watching for exactly the kinds of impossibilities that refuse to be averaged away. But that is not this night. This night, 3i Atlas behaves like physics, a visitor whose story is written in chemistry and sunlight, not firmware. It's worth saying out loud that this is not a consolation prize. A postcard that isn't a love letter is still a postcard. It still proves there's a city you've never seen with weather you can taste in the ink. The absence of a beacon doesn't make the message smaller, it just changes what it's about. If it were a machine, we'd expect the universe to tell on it. Sharp lines, sharp edges, sharp timings. What we have are soft signatures, dust gas, a slouching light curve, a tail, and its ghost acceleration that breathes with the sun. In the ledger, where hypotheses are scored against evidence, the natural column fills itself line by line. The extraordinary column waits its turn empty but ready as it should be. The discipline is to keep both columns open and write in ink only when the sky tells you to. For now, the sky is saying this, not a probe but a postcard from another star's cold vineyard stamped in CO and CO2, signed by no one and thus by everyone. That is not less wondrous. It is the kind of wonder that stays true in the morning. If 3i Atlas has taught us anything, it's not only how to look up but how to listen well. Because every time a new cosmic mystery arrives, the first thing that fails is not the telescope, it's the microphone. The way we tell the story matters as much as the discovery itself. When a strange object flashes across the sky, the data belong to science, but the story belongs to everyone. The astronomer chasing spectra at 3 a.m., the headline writer racing a deadline, the viewer scrolling between dinner and sleep, all are connected by a thread of curiosity. And yet between the data and the audience, something delicate can fracture. One misplaced word, alien, impossible, defying physics, can turn nuance into spectacle. The challenge is not to kill wonder, but to keep wonder honest. Here is the quiet code of ethics that the cosmos keeps trying to teach us. 1. Curiosity before certainty. Science is not a courtroom that demands verdicts. It's a conversation that deepens with questions. The most courageous phrase in research is not eureka, but we don't know yet. That yet is the heartbeat of discovery. When media or creators skip it, when they leap from anomaly to conclusion, they trade truth for entertainment. And in that trade, both suffer. If we tell audiences that every mystery must resolve into proof, we rob them of the beauty of process, the slow dance between evidence and imagination. 2. Translate, don't flatten. A scientific uncertainty isn't vagueness, it's a carefully measured confidence interval. When a paper says 10% probability, that's not a tease, it's the outline of a question still alive. Translating that into headlines that scream "scientists say it might be aliens" turns statistical humility into hype. Instead, we can translate uncertainty as possibility with discipline. Invite people to wonder why the odds are what they are. Ask what would change those odds. A question framed well is more magnetic than an answer shouted. 3. Context is oxygen. Every discovery has ancestors. Oumuamua didn't appear in isolation. It followed Borisov, which followed centuries of comet studies, which followed Galileo. Without context, every object becomes a miracle. With context, it becomes a chapter. Good storytelling anchors astonishment to continuity. It shows that we are building a ladder, not chasing lightning. 4. Avoid the theatre of certainty. There's a reason scientists hedge. They have seen how quickly excitement turns to ridicule when data evolve. The public deserves enthusiasm but not overconfidence. When you say confirmed alien probe and it becomes ordinary comet truss fractures, that fracture hurts future science more than any funding cut. So say instead, here's what we see, here's what we suspect, here's what remains unknown. Honesty does not dull excitement. It makes excitement sustainable. 5. Keep the human scale visible. Behind every dataset is a person tired, hopeful, fallible. When media show scientists as disembodied experts or conspiracy gatekeepers, the public loses empathy and turns skepticism into cynicism. Show the long nights, the calibrations, the laughter in control rooms. Show that science is human craft, not institutional decree. Then skepticism becomes collaboration. Help us test this, not. They're hiding it. 6. Distinguish wonder from fantasy. Wonder is what happens when the unknown invites humility. Fantasy is what happens when the unknown is forced to flatter us. When we frame every mystery as proof that we're special, the chosen species to witness the gods' return, we shrink the cosmos to fit our reflection. But when we allow it to remain vast, indifferent, and beautiful, we expand with it. Tell stories that let listeners feel small and connected. That is the paradox that keeps awe alive. 7. Let data sing. Numbers are not cold, they are verses in a longer poem. The curve of a comet's brightness, the slope of a spectral line, each is a melody that can move hearts if played clearly. You don't need exaggeration when reality already composes music. A good narrator is less a magician than a conductor, guiding the audience through rhythm and silence, letting tension build, releasing it not with spectacle, but with understanding. 8. Build literacy, not allegiance. Teach the audience how to weigh claims, how to read uncertainty, how to spot overfitting, how to appreciate replication. When people understand the scaffolding of truth, they don't need to be told what to believe. They can listen critically and wonder freely. That's the equilibrium between skepticism and awe that science communication should aim for. 9. Remember that silence is part of the song. In a world addicted to immediacy, no conclusion yet feels like failure. But every real discovery passes through a quiet phase, the months when data are still raw, when the signal is half buried in noise. That silence is not emptiness, it's gestation. Tell audiences that patience is part of the method. Invite them into that waiting room where the universe is still clearing its throat. 10. Gratitude over sensationalism. The difference between clickbait and wonder is gratitude. One uses mystery to feed appetite, the other pauses long enough to say thank you. Even when an anomaly resolves into the ordinary is miraculous. A CO2-rich comet from another star is not a disappointment. It's a revelation of how vast chemistry can be. If we teach that to the public, we inoculate them against disillusionment. So perhaps the lesson is simple. The goal is not to make science louder, but to make listening deeper. Curiosity is a fragile thing, it grows best in trust. We don't need to promise aliens to keep people awake. We only need to promise honesty and deliver it with poetry. Because storytelling is the bridge between data and meaning. And when told with care, even a whisper from the edge of the solar system can carry across the world. We can let it sing without distortion, let it breathe without exaggeration, let it remind us that truth spoken softly can still shake the stars. In the end, the comet leaves. It always does. Its light fades into the dawn, the data files are archived, and the debate quiets down into conference coffee breaks and footnotes. But something remains not in the sky, but in us. Whether 3C Atlas was a frozen shard or an artifact that only pretended to be ordinary, it has already changed us because we looked. And looking is never neutral. It pulls us into the story of motion, of chemistry, of time, the quiet story that every grain of dust, every cell, and every star has been telling since the beginning. Think of what it means that this visitor existed at all. That somewhere in the cold orbit of another sun, long before humans had names or questions, a fragment broke free. That it drifted through interstellar night for 1 million years untouched, except by gravity and starlight. That it crossed the galaxy's arm, found our little solar system by chance, and for a brief moment brushed our awareness. That the light bouncing off its dust entered our telescopes, and through those photons entered our eyes. For a moment, a piece of another world touched our retinas, and that means in a small way we have already met. If it was natural, then it is proof of kinship, not loneliness. It tells us that the galaxy is fertile, that planetary systems give birth not just to worlds, but to wanderers, travellers who carry chemistry, like pollen from one star's garden to another's. It reminds us that the atoms in our bones were once part of the same cosmic traffic carbon. From one cloud oxygen from another, hydrogen born in the first minutes after time began. Everything that drifts, lives and dies does so under the same patient laws. We are each of us a version of a comet spinning, sublimating, shedding light for a while, then returning to silence. And if it was something more, something built, the meaning still circles back to the same place. Because even then it would confirm not our uniqueness, but our continuity. It would mean that curiosity survived somewhere else long enough to reach out that wondering is not an accident of this one planet, but a universal impulse as natural as gravity. In both stories, whether shard or ship, the moral is shared. We are part of a universe that notices itself. The difference between artifact and comet in the end may not be as large as it feels. Both are vessels of memory. One carries chemistry, the other intention. Both are born from the same cosmic dust. Both move by sunlight. Both remind us that to exist is to travel, to erode, to shine, to leave behind a trail that others might follow and read. As 3i Atlas slips back into the outer dark, astronomers will keep refining its orbit, its composition, its brightness curves. The rest of us can do something simpler. We can pause. We can feel the faint hum of connection between a telescope dome opening under cold stars and the quiet heartbeat inside our ribs. Both are instruments listening to the same night. Both are made of atoms that once drifted between stars. And both are awake to wonder, however briefly. Maybe that's the quiet answer the comet came to give, that the purpose of mystery is not always to be solved. Sometimes it's to keep us company, to remind us that curiosity is a kind of communion, that even in our smallness we belong to the same unfolding pattern motion, heat, decay, renewal. The same laws that carry 3i Atlas through the sun's light carry the breath that fogs our windows in winter. The same energy that glows in its coma glows behind our eyes when we look up. So let the headlines fade. Let the arguments rest. In the soft hum of space between signals, there is still the echo of a visitor, silent now but not gone. And if you listen carefully, you can still hear what it was saying all along, that the universe is vast enough to be strange, gentle enough to be understood, and patient enough to wait for us to notice. Tonight, as the world spins and the instruments sleep, take a breath and let your thoughts drift with it, that small traveller, now somewhere beyond Mars, cooling in shadow, still following its unbound path. You don't need it to be alien for it to feel miraculous. You only need to remember that you share its materials, its motion, its time. You are made of the same story written in light and dust. And perhaps mystery itself, the part we can't quite name, is how the universe keeps us awake to wonder. Good night, traveller. Good night, sky. Good night, us.